I welcome Professor Prakash Kotecha sir for this first inaugural talk. So before sir will discuss about some of the topics, let me introduce Prakash Kotecha sir. So Professor Prakash Kotecha is currently working as a professor in the Department of Chemical Engineering at IIT Guwahati, Assam, India. He received PhD degree from IIT Bombay in 2008, MTech degree from CIT Coimbatore, India, BTech degree from Pondicherry Engineering College, Pondicherry, in the field of chemical engineering. His teaching and research interests are applied optimization and computational intelligence. He received several travel grants from DST and Dr. Dr. A.V. Ramarao Foundation Best PhD Thesis and Research Award in the year of 2011 and PhD Student Excellence Award. Sir is having a number of research publications in various reputed international journals and conferences. And you can find SAR's numerous lecture in NPTEL video by visiting SAR's website. I'll share the link with you. So with this short bio, I request Professor Prakash Kotecha sir to start the session.
Good evening, everyone. I am sorry that there was some delay from my side. Unfortunately, something unexpected came up. So just give me a minute, please. Let me just download a couple of things. So are you able to see my slides?
Yes, sir.
Okay. So my setup is not fully functional. So we'll have some issues here and there. Let's see how far we are able to sort it out. Let me connect to another machine also. Let's see if that works. Okay, fine. I think so now we should be fine. So I'm going to talk about introduction of optimization. So the lecture series which sir said is, so whatever I'm going to teach is part of an NPTEL course that I have. So in that course, what we do is we look at few meta-heuristic techniques. So optimization techniques can be classified into two types. One is mathematical programming techniques. Another is meta-heuristic techniques. So meta-heuristic techniques.
Sir, we are not able to see the presentation.
Oh.
Excuse me, sir.
Yeah.
Presentation we are unable to see.
1 second.
1 second. Slides are not visible.
1 second. 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 1 sec How about now? Are slides visible now?
No, sir, it is not
No,
visible.
sir. No, not it.
So is the screen visible?
No, sir.
Now it is visible, sir.
Okay.
Okay, sir.
So optimization techniques can be broadly classified into two types of techniques. One is called as meta-heuristic techniques and another one is mathematical programming techniques. So in meta-heuristic techniques, some of the techniques which you are going to see as part of this FDP, or some of you would have already done few of these techniques. For example, genetic algorithm, particle swarm optimization, differential evolution, and artificial bee colony optimization are kind of pretty standard algorithms which you might have studied some time back. Right. So FDP, this FDP, usually what I have seen is many times people are already aware of the technique. Their primary point is how to use them in their application. So 4 or 5 times when I have given lecture over here, primarily the conversation tended to go over in that direction. But I will go as per what I have planned. But in between, if you have some questions, please ask the questions. And in mathematical programming technique, we have linear programming and mixed integer linear programming techniques. So in this lecture, if time permits, I will talk about one particular problem called as production planning problem. So that will give you a flavor of what is a real life optimization problem. And knowingly or unknowingly, most of us would have kind of worked on optimization problem when we have done this regression. So many of us would have done an experiment wherein we are changing x, observing y. We would have got such data points, and then we would have said to Excel that fit a best fitting line. So some line you would have given straight line. If you have selected y is equal to mx plus c, it would give you a straight line, and then it will also give you r square, some value of r square. So this is pretty much most of us would have done. So that is actually part of optimization. In fact, that is the primary use of optimization is to minimize the error. So here I am trying to fit a line such that the error between what is the value given by the line and the actual observation. So this distance, the sum of square of this distance is to be minimized. So that's some application that most of us would have come across at some point of time. Okay, so I think so. Parnivel sir is okay.
Sir, I'm
Okay. So these are three types of problems which many of us would have come across, standard optimization problem. So one is called as.
so sorry to disturb you, sir. I'm unable to view your presentation, sir.
Is that the
It's
case?
visible, sir. It's visible.
No, sir,
Presentation is visible,
Now it's
sir.
It's visible, sir.
Sometimes
Clearly.
due to network connectivity, for certain people it gets it
Okay.
may not be visible, sir. But for us it is visible.
Okay. Thank you,
Okay,
ma'am.
sir.
Yes, it is visible, sir, but previously there were no slides, sir. Now it is visible.
Okay.
Okay.
So this is a traveling salesman problem. Very often you would have come across the term TSP, traveling salesman problem. So in this, a salesperson wants to visit few cities, city A, B, C, D, E. So let's say 5 cities, and the person does not want to revisit a city, right? In that case, what is the minimum cost which is to be minimum cost is what is to be found out. So what route should the person take? So should he start from A, go to E, and then go to D, and then go to C, B? So what is the sequence of path that the person has to take so that all the cities are covered. So that's a classical optimization problem. And then we have a problem called a knapsack problem. In some way, this is a problem that all of us, when we are flying or traveling, we would have come across this problem, that you have limited space, like your airline has said 15 kgs, and then you are trying to see what best articles to take. So in the case of a hiker, he wants to go from the bottom of the mountain to the top of the mountain. So he wants to carry few items. So which are the items that he would like to carry, such that the maximum total value, the value of the whatever he is carrying is maximum while satisfying the weight constraint. So this is a problem wherein there is a constraint. So the person cannot carry more than a particular amount. So there is a weight constraint, but the person wants to maximize the total value. So this is also another classical optimization problem called as knapsack problem. This third problem is something that many of you may not have come across. This is called as a feasibility problem. So there are two types of problem. One is optimization problem and another one is feasibility problem. So feasibility problem is a subset of optimization problem. So in this case, I am not looking to maximize or minimize. So the problem itself is there are these 4 colors and there are these 6 countries shown in the map. So the objective is that we want to color the countries so that no pair of neighboring countries have the same color. So the countries are distinctly visible. Right? So here I am not maximizing or minimizing something, but I want to satisfy few set of constraints. So this is also an example of feasibility problem. Sudoku problems are example of feasibility problem. So I have 81 variables, right? 9 and 9 by 9, 81 decision variables. So if I call them as x1, x2, x3 all the way up to x81, then I have a constraint that the number has to be between 1 and 9. All of these numbers have to be between 1 and 9. So this is called as decision variable. So I need to choose what should be the value of x1. And I have the freedom to select anything between 1 and 9. So 1 and 9 are called as the lower and upper bound. So this is lower bound, this is upper bound, and I have 81 variables. So in this case, for example, x2, if I call this as x2, x2 is already fixed. So it is no longer a decision variable. The value is fixed, x2 is equal to 7. Right? And on top of this, there are some constraints. So for example, one constraint is x1 should not be equal to x2, x1 should not be equal to x3, x1 should not be equal to x4 to take care of this row. Similarly, I write constraints to take care of this column, that no two variables take identical value. And then there are constraints for this. So let us say I have these variables as x1, x2, x3, x4, x5, x6, x7, x8, x9. Then within these 9 variables, the value should not be the same. Right? So this is again any algorithm. Just 1 second, let me get rid of that. So this is a typical feasibility formulation. So whatever constraints I had, we are not going into look into how this equation arrived, but it basically says the same thing, that across row, across columns, across this 9 by 9 square, the values are not repeated. Right? So this is a particular mathematical formulation for this Sudoku problem, and this is its corresponding code. So this set of equations I can solve using multiple techniques. One is what we were discussing, mathematical programming techniques. The other one is meta-heuristic techniques. And there is a third class of techniques which do not fall in either of them. That is known as constraint programming. One such technique is constraint programming. So this, what the code that you are seeing, is part of constraint programming. So this slide is not necessarily to teach you how to solve the Sudoku problem. It is just to give you a flavor as to what all things can be done by the algorithms that you are going to study as part of this FDP. So this is formal introduction of optimization problem. So in case someone is totally new to optimization, this is probably the first slide. So in optimization, I need to decide something. Because I need to decide something, I can decide it in a good way or bad way. right? So what I am being said is decide on these variables subject to maximizing profit or minimizing the time taken to complete a task. That is called as my objective function. So primarily what I have is decision variable. If you do not have the liberty to make a decision, then there is no optimization problem. So for example, if someone writes like this, maximize a is equal to 3, then there is no optimization problem, right? So I can say this is a constraint, this is objective function, but it does not make any sense because there is no degree of freedom, right? There is only one variable, and that too it is not a variable, it is a parameter because its value is a priori known. Decision variables are those wherein, let's say I have x and I have been given the freedom to select the values of x from 5 to 10. Right? So that is what is decision variable. Classical example is if you want to fly from your place to let's say Delhi, you get a range of options, right? You can take an Air India flight or an Indigo flight. Indigo flight also you can take a 3 o'clock flight, 7 o'clock flight, 10 o'clock flight. So that is your decision variable. Your decision variable is which flight to take. The options that you have, that forms the domain. So in this case, what I'm writing is a continuous domain. X is between 5 and 10, but you can also have like this over here what you have. So one of it can be my set. So this is my flight 1, flight 2, flight 3, flight 4, and flight 5. So these are the 5 options that I have, and X has to take a value from this. So what is F1? This is F1, this is F2, this is F3, F4, F5, F6. Right? So very often this is a confusion, that especially when a big problem is given. So a big problem is given, then you need to identify what are the values which are already known to you. If a value is already known to you, uniquely fixed, that cannot be a decision variable. Decision variable is where you have degree of freedom, that you are allowed to choose between a lower and an upper bound, or from a set like this. So those are decision variables. And then you have objective function and constraints. So both of this objective function and constraints are relation of decision variables. Objective function is something that you are trying to improve, either maximize or minimize, and constraints are something that you need to satisfy. So for example, in this case, I have 5 flights, but if you tell me that I need to be there by 12 o'clock tomorrow morning, then all of this five are no longer applicable to me, because you have put a constraint. Some of these options are taken out, right? So that is what is constraints. You have a large number of options, but the set of solutions which satisfy all the constraints may be considerably smaller than the entire range. So decision variables broadly can be of 3 types. One is continuous, and then semi-continuous, and then discrete or sets. So discrete or sets is something that I showed you in the previous slide, that I have 5 flight options to take, which one to take. So that is a decision variable, and my options are discrete, right? And then I have continuous variables. So when I write x less than equal to 5 to 10, that means x can take any value between 5 and 10. There are infinite values between 5 and 10. So x is then a continuous variable. Sometimes the variables can be semi-continuous also. So for example, this one shows semi-continuous variable. So the variable x1 can take any value between 5 and 10, and can take any value between 15 and 20. It cannot take anything greater than 10 and less than equal to 15. So this zone is not permissible. Between 5 to 10 is allowed, 15 to 20 is allowed. So obviously, the first question is, why would I get such, where would I get such a type of variable? But these variables are far too common. So for example, let us say, I have the freedom not to prepare tea, right? I need to prepare tea or not prepare tea? I have the freedom not to prepare. But if I decide I have to prepare, now I cannot say I will prepare tea 0.1 ml, right? So if you are preparing, that means you are going to go to greater than 0, but then it cannot be immediately 0.001, right? For the sake of writing, I can write the amount of tea that I am going to prepare is between 0 to 10 liters. But if I ask you to prepare 0.001 ml of tea, that is not going to be feasible unless you have very specialized set of equipments with you. So very often this continuous variable, semi-continuous variable appear in real life. Okay, so far, if there are any doubts, I can clarify.
Sir, how about the colors? If you are having some specific colors
So that comes into
in a
discrete
semi-continuous
or
variable, right?
no, that is not semi-continuous. That is discrete or sets. So for example, this one, that map coloring problem. So this is a set, right? So I can take either blue or white or yellow or green. So that is a set.
Okay. Okay, I got it.
Yeah, okay. Thank you, ma'am. Any other question? Let me just see, someone had typed something. Okay, this is just. So objective function, just like your decision variables, your objective functions can either be continuous or semi-continuous. So for example, this shows a continuous objective function that as my decision variable changes, my objective function has a value. So objective function is nothing but a relation of decision variable. So for example, if I have two variables, let's say this x1 square plus sin x2 is an objective function, right? I have x1
Sir, your
and
screen, excuse me, sir, your screen is not there.
I didn't disturb anything. So
It's shared.
No, I am able to see.
It's visible. It's visible, sir.
okay, yeah.
Because we're having problem, better to log in again. I think screen is visible, sir. Thank you.
Okay.
Okay.
Thank
Okay,
you.
sir. Then I am again logging it. Okay,
Oh.
thank you.
So in this case, I have x1 and x2 are my decision variables. I need to decide what should be the values of x1 and x2. And let's say for some reason, I want to minimize this function, right? So minimize f of x. So this is my objective function. I have two variables, x1 and x2. And I'm looking for a value of x1 and x2 such that this function will have the minimum possible value. So that is what is objective function. I think so most of the algorithms you would be doing as part of this FDP would be thought for a minimization problem, right? So the presumption is that you want to minimize f of x. But what happens if in real life I end up with a problem of maximizing, let's say, f of x? I have a problem maximize f of x, and the algorithm which I have can solve only minimization problem. So in this case, what we can do is that instead of solving maximize f of x, we can solve minimize minus f of x. Right? So trivial example is given over here. So for example, the maximum of this function and the minimum of this mirror image. So this is f of x and the top one is minus f of x, or the other way. This is f of x and this is minus f of x. So these are mirror images, and the place where the optima occurs, the place where the minimum of this function occurs and the place of where the minimum of this function occurs, that is only x star, right? That would be the same point. So the set of decision variables would be the same. Obviously the objective function would be here minus f of x. This, let's say this is minus 5. So this will be plus 5, right? But the value of the decision variables, there are two things. One is that I am interested in what is the value of the decision variable. And the second thing is, at that value of decision variable, what is my objective function, right? So once you find out what are the decision variables, then the value of the objective function is straightforward. You just dump it into this objective function and you will be able to get the value of the objective function. So what is more important is the value of the decision variables, right? So for example, someone asks me that what should I do so that I get my profit maximized, right? Then I am supposed to tell what should the person do, right? So that is the decision variable. If I blindly say, oh, you will get a profit of 20,000 rupees, then obviously with that is an important information, but with that information, the person would not be able to do anything. So I need to say that if you do this, step A, step B, step C, so that is the decision variable. If you take this decision, this decision, this decision, then you will incur a profit of 1,000 rupees, 20,000 rupees, whatever that value I previously said, right? So the point is that whether it's a minimization problem or a maximization problem, the same algorithm can solve both the problems. So typically algorithms are written for minimization problem. If you have a maximization problem, you transform your problem to a minimization problem. So I am not saying for me what was given is maximize profit, and now the problem that I will solve is minimize profit. I am not saying that. What I am saying is, if I have been asked to calculate maximize profit, what I will do is I will minimize minus profit. So the solution of minimize minus profit and the solution of maximize profit would be one and the same with respect to the decision variables, this x star. And that is what I am primarily interested. And then you have feasibility problems. So over here I have a feasibility problem, same Sudoku problem. So in these cases we do not have any objective function. As such, there is no objective function. You can always create dummy objectives. So for example, if I have an optimization algorithm and if I want to solve this particular problem, you can say, like, for some reason you can say minimize x1 subject to all your constraints, right? So that will give you one of the many solutions which are there for that particular Sudoku problem. So this is all about objective function. Constraints are broadly divided into two types. One is inequality constraints. The other one is equality constraints. Inequality constraints are usually resource constraints, that I have a maximum of 10,000 rupees. Decide such that you don't spend more than 1,000 rupees, right? So anything less than 1,000 rupees is fine, but I should not go more than 1,000 rupees. So these are such constraints. So they are typically denoted by g of x is less than equal to 0. So obviously, if I have g prime of x which is greater than or equal to 0, I can multiply by a minus sign. Let's say this is less greater than or equal to 5. I can multiply by minus sign. So now minus g of x is less than equal to minus 5. So greater than constraints is also fine. Less than equal to constraints are also fine. So from one form to the another form, I can multiply by a minus sign and reverse the inequality. So those are inequality constraints. So here, if I consume less than what is available, that is fine. So it's like going to the market with 1,000 rupees and trying to buy a pair of shoes, right? So if I'm able to do it in 800 rupees, that is fine. It's not necessary that I need to spend exactly 1,000 rupees. All 1,000 rupees needs to spend. That is not correct. That is not required. So those are inequality constraints. Equality constraints are the other way, that if I'm taking 1,000 rupees, I need to exactly spend 1,000 rupees, right? It's not like I can, even if I'm done with 999, it is fine. That's not the case in equality constraint. So where it appears is equality constraint, usually in balances. So for example, if I have a process flow diagram and what is coming here, let's say it is like this. So let us say this is my x1, this is my x2, and this is my x3. So those three are my decision variables, let us say, right? In this case, what happens is that my x1 should always be equal to x2 plus x3. Otherwise, what is happening is I am accumulating it inside x1, right? So these are places wherein you will have equality constraint, that it has to be precisely satisfied. There is no flexibility to do less than what is available. Right? So that is inequality and equality constraints. Then we have two type of solutions, a feasible solution and an infeasible solution. A feasible solution is a solution which satisfies all the constraints. So if I have 1,000 constraints, the solution should satisfy all the 1,000 constraints. If it satisfies all the 1,000 constraints, then I can call it as a feasible solution. Infeasible solution is there is at least one constraint violation. So again, I have 1,000 solutions. I have a new solution with me. Even if it satisfies 999 constraints, even then it is an infeasible solution. Like typically for many of us in the old schooling system, it is like I have to pass in all the 5 subjects, right? So does not matter if I score 100 out of 100 in 4 of the 5 subjects, and in the 5th subject I score 34, and the and the passing mark is 35. So my total can be 434 compared to another person who has scored 35 in all the subjects. So that person is considered pass, right? Because that person has satisfied that constraint, that mark should be greater than or equal to 35. So that person will be declared, will be promoted. I'll be detained because I have scored 34 in one of the subject, despite the fact that I have scored 100 out of 100 in 4 other subjects. So no matter how good the objective function is, if your solution does not satisfy a constraint, then that solution is something that you cannot even implement. Right? So objective function is important. We always run behind that objective function, but not at the cost of violating the constraints. So constraints are far more superior than your objective function. Okay, so this is an example, more of whatever I said. It's just the same thing. So I have two solutions, 3,10 and 8,6. So my x1 and x2 are decision variables. So if x1 is equal to 3, x2 is equal to 10, that is solution 1. So for this solution, if I calculate the objective function, it turns out to be 7.05, and this part, the right hand side, turns out to be 70.69. Right? So this is S1, whereas this is S2. The objective function is 16.34, and I am minimizing here. Right? Since I am minimizing this is better than, so S1 is better than S2 because S1 has a lower F1, but S1 would not be selected because it does not satisfy this constraint. This is not greater than 300. Right? So this is an infeasible solution. So though it has a good objective function value, I will not choose this solution if I have this solution available. So any doubt till that thing? So previously what we have basically done now is just establish the components of an optimization problem. So optimization problem broadly has three important things. One is decision variable, then the constraints, and then the objective function. Objective function is something that I want to minimize or maximize. Decision variables are the decisions which are left to me. As a person who is solving the optimization problem, I am being asked what are the best set of decisions to minimize or maximize this, and my decisions should obey the constraints. So if I have been told that whatever this value should be greater than or equal to 300, I need to ensure that whatever solution I give at the end of the day is actually greater than or equal to 300. So maybe if you want, I can stop for a minute or two if you want to just recollect whatever has been done, and then I can continue. There is no point me teaching some 50-60 slides if you have issues in the 10th slide itself.
No, sir, clear. It is very clear.
Okay. So let me just first finish this part and then come back to this. So since now we have seen variables, objective function, and constraints, right? So variables, there are broadly two types. One is continuous and another one is discrete. Obviously, this classification does not take care into effect the semi-continuous variable. So if I have semi-continuous variable, I'll do something to that variable so that it becomes discrete. So I'll show you an example. It's a little lengthier example. So that's why semi-continuous variable is not over here. So variables, they can either be continuous or discrete. Objective function and constraints, both are mathematical functions, right? So we can classify them whether they are linear or non-linear. So objective function, linear, non-linear, constraints, linear, non-linear. So the first set of problems is called as linear programming or LP problems. So LP means it says linear. L stands for linear. So obviously the objective function has to be linear. It does not permit non-linearity. And similarly in constraints, it only permits linear constraint. It does not permit non-linear constraints. And when I say linear programming, I am only telling about the nature of the objective function and constraints. I am not telling anything about the variables. If I don't tell anything about the variables in the name, that means they can only be continuous. So no discrete, only continuous variable. So these are called as linear programming problems, LP problems. Then we have NLP problems. So again, I am saying non-linear, right? Non-linear is with respect to the functions. So yeah, I can have non-linearity in objective function. I can have non-linearity in constraints, and I can also have linear function, linear constraints and linear objective function. That is fine. So let us assume a case wherein I have 10 constraints and one objective function. So if 9 of the constraints are linear and I have one non-linear constraint, even then it is a non-linear programming problem. Right? So non-linear programming problem, NLP. Again, in both the cases, I am not telling anything about the nature of the variable in the name of the problem. So it is by default continuous. Then I have integer linear programming. So here I am explicitly telling what is the nature of the decision variable, integer. So that means I am not allowed to have continuous variable. I am only allowed to have discrete variable. My objective function can be linear because it is linear programming over here. So the objective function also has to be linear and the constraints also have to be linear. So that is called as integer linear programming. And then this should be very evident, mixed integer linear programming and mixed integer non-linear programming. So MILP and MINLP. So mixed integer, which means some variables are continuous, some variables are discrete, and I am saying linear programming. So that means non-linearity is not allowed, right? The constraints and the objective function need to be linear. And then finally, I have mixed integer non-linear programming. So when I have mixed integer non-linear programming, everything is allowed. So linear constraints, linear objective function, non-linear constraints, non-linear objective function, all of them are allowed. And the variables can be continuous. Some variables are continuous and some variables are integer. So if there are no integer variables, then I land up here in non-linear programming. So this is classification of optimization problems. There are various ways to classify. This is based on the nature of the variables and nature of objective functions and constraints.
So 1 second, can you please give me an example for linear programming and non-linear programming? Like you have said, like for linear programming, it is like data is continuous. I'm sorry, variables are continuous and discrete.
Variables are continuous and my objective function and constraints are linear. So for example, this problem, if you see, obviously I understand, I have not discussed it. I'll write a simpler problem, but before that, I just wanted to show this. So here X is a decision variable. So in all of this, if you see, X is not occurring in terms of multiplication. So this is a linear equation. Xijk is linear. The summation only tells x1 plus x2 plus x3, right? It does not make it non-linear. So here, if you see, everything is linear. So you wanted a practical example of integer linear programming. This is a practical example of integer linear programming, wherein all my constraints are integer, all my variables are integers. So this is an example of integer linear programming. But if I want, let's say, continuous linear programming problem, right? I think so I would have it. So, yeah. So this is an example of linear programming. So I have two decision variables, x1 and x2. My objective function is minimize 4x1 minus x2, and these are my constraints. Right? So this is an example of linear programming problem.
Okay, sir. And in case of variables which can be both continuous and discrete.
Okay, so the way I explained, maybe that has caused a little bit of confusion. A single variable cannot be continuous as well as discrete. So one variable is continuous. So let's say x1 is between 5 and 10, and x2 is, let us say, discrete, as in like it can take 5, 8, and 9.
Okay, sir.
Let's say x2 is India, Sri Lanka, and Malaysia. Right? So these are my three choices. I can do my annual vacation in India, Sri Lanka, or Malaysia. So those are my choices. So one variable is continuous and the other variable is discrete. The same variable cannot do both the job.
Okay, so among the decision variables, one of the variable can be continuous and other variable can be discrete.
Yeah.
Thank you so much, sir.
Thank you. Any other questions?
So, how can we decide that which optimization problem will fit for the particular situation? So, is there any criteria or any to choose which optimization problem?
So I'll indirectly answer that question because there is no direct answer as such for that question. So maybe this is a 1.5 hour lecture. So out of this 90 minutes, if there is 5-minute material which you want to keep in your memory forever, this is one thing. right? Linear programming, non-linear programming, ILP, mixed integer linear programming, mixed integer non-linear programming. So this is something that you should know as a person who knows a little bit about optimization, right? So the second question is what madam rightly asked is that I have a problem. So when I say I have a problem, I never have a problem like this. No one gives me problem as I showed in the previous slide. They don't give me equations, right? So for example, no one comes and tells me solve this problem, because if they already have this, they don't need me. They only need a software, right? So what we usually get is a description of the problem, right? From the description of the problem, we are supposed to formulate it. Now when I am formulating it, I will try to, as much as possible, right, try to formulate this as linear programming. But sometimes you cannot formulate. No matter what you do, you will not be able to formulate it as a linear programming problem. So for example, let us say how much money to spend on my vacation. So that is a continuous variable. I can say anywhere between 10,000 to 50,000 I am willing to spend. But the moment you say that the choices, the cities you can visit is Delhi, Bombay, Calcutta, now I have made my optimization problem. There is an integer variable. Now I cannot remove that integer variable ever, right? That is inherently part of my problem. Because that integer variable is there, now I will not end up with a linear programming problem.
Okay.
Is it clear?
Okay. Yes.
Right. So sometimes some of you, if you are from let's say something I calculate I square r, right? So for example, my current is also continuous variable. So my current is a decision variable that I need to decide, and resistance is also given to me, right? That I am allowed to change my resistance also. Current also I can change, resistance also I can change, but there is this parameter called as, let's say, x. Now, if this relation has to be satisfied, then I need to include this relation. And if I and r are my decision variable, then I have introduced a nonlinearity. So this is from the physics of the problem. I cannot now say I square r. I cannot, for my convenience, say that it is I plus r. Right? So because the nature of whatever you are trying to capture is nonlinear, because of that, you inherently get nonlinearity. So the first example I gave is with respect to the decision variables, that you will not always be fortunate to have only continuous variable. Now what I am saying is, you will not always be fortunate to have linear constraints. And so it depends upon the problem that you are trying to model. Did I answer it a little bit to what you wanted?
Yes, sir.
Okay.
Yes, sir. Thank you.
Fine. So any other questions? Yes.
So can you please get back to that slide, sir?
Which one, ma'am?
One you just stopped with earlier slide. Variables.
This one?
Yes, sir. So in NLP, we have an objective function which satisfies both linear and non-linear properties.
So just 1 second. Again, there it can be slightly misleading. So I have only one objective function. It is permitted to be either linear or non-linear. So a function cannot be linear as well as non-linear. So
Okay.
it is fine if it is linear. It is fine if it is non-linear.
Okay, sir. Okay.
And constraints also same thing. That some of my constraints are linear, some of my constraints are non-linear.
Okay. Thank you, sir. Thank you, sir.
Tai Reddy. The person has raised hand. Okay. Fine. Okay. So ideally, again, what I am saying, if you kind of start working in optimization, definitely you will feel at one point of the time you will understand that what I am saying is not fully correct, right? But as a first class on optimization, if just 1 second, let me get rid of this markings which I have done. Okay. So if I have a linear programming problem, so in this case I have a linear programming problem, why linear programming problems are good to solve, right? So when you are solving an optimization problem, there are two things, right? One is I want to get the best solution, right? What is called as globally optimal solution, that there is no other better solution than the globally optimal solution. So I am interested in finding out that particular solution, right? So that I am calling it as quality of my solution. The second one is how fast I am able to find out, right? So let us say if there are two algorithms, both of them are capable of finding out the best solution, then I am interested in which algorithm is able to find out fastest, right? So that, in my personal opinion, that is a secondary criteria. Which is faster is secondary criteria, because most optimization problems are offline. Like it is not like every 2 minutes, every 3 minutes I need to make a decision, or every 2 seconds, 3 seconds I need to implement a decision. Optimization again is not something that can exist standalone. Optimization is more like a computer. You can have a fancy computer at your house, but as long as you don't use it, there is no purpose of it. So same thing, optimization occurs, you are solving a bigger problem. In there is an optimization problem, and when you solve the optimization problem, you get the values of the decision variables, which you will take and go and do something with those values, right? In an optimization course, for example, for this problem, I will stop saying that x1 is equal to 5, x2 is equal to 10 is the best solution. I'll help you find out the solution. But why was I interested to find out the values of this first, right? Because I want to implement them. So there is a second stage. uh, Optimization is the middle stage. I have some problem. From that problem, I came down to this equation. How to solve these equations, that is what is done in an optimization course. We teach you technique. Given a problem like this, how will you solve it? But after solving also, you are going to go and implement it somewhere, right? So optimization is occurs in middle. So that way, most of the optimization problems are offline optimization problem, right? Let us say I want to design my supply chain. I have 10 warehouses, and from which warehouse, where will I supply? To which customer will I supply? That is an optimization problem. Do I want to solve it very fast? The answer is yes. I want to solve it as fast as possible. But am I willing to compromise on the optimality, the quality of the solution? My answer is no. Instead of 5 seconds, take 10 seconds to solve the problem, but give me the best possible solution. Okay? So there are two things. When you have linear programming, LP and MILP. So for these two classes of problem, there are algorithms which will guarantee you globally optimal solution. That is not there for NLP and MINLP. So if you end up with a nonlinear programming or a mixed integer nonlinear programming, there are no algorithms. There are algorithms which will give you a solution, but it will not come with a guarantee that this is the best possible solution. So that's why if you are able to formulate your problem as LP and MILP, it is good, right? Otherwise, you will be able to solve NLP and MINLP, but there won't be any guarantee that this is the best possible. This is the best possible solution.
So since because it is an NLP, we that there is no possible solution.
I'm not saying that if it's an NLP, there is no possible solution. I am only saying that the solution does not come with a guarantee that it is the best possible solution. Right? So, for example, let us say I have this function. Right now, and I am interested in finding out the minimum possible value. So this is also a minima because the gradient vanishes here. This is also a minima. But what I am interested in is this solution.
Yes.
Right? So if it is a one variable problem, so this is f of x, this is x. So if it's a single variable problem, I would plot and see where the minima occurs. But if I have a problem with 1,000 variables, I cannot plot and see where the minima occurs. Right?
Yes.
So then I am using an algorithm. That algorithm does not come with a guarantee that it will always find this particular solution. It may end up finding this solution, or it may end up finding this solution.
Okay, sir. Okay, sir. Thank you.
Okay. So what I was saying is LP and LP and MILP can be solved to globally optimal solution. It may take a little bit longer in some cases, but it can be solved to globally optimal solution. So I would prefer my problem, if it lands up as an LP or MILP, I would be happy about it, because at the end of the day, I will be able to solve to the globally optimal solution. The guarantee for MILP is because it only basically solves a series of LPs. So MILP solves many LPs. We are not going to see as part of this lecture, but in case if you are interested, you can look around. You will be able to see a technique called as branch and bound. So in this, what happens is you solve a series of LP to end up solving your actual MILP. And for LP, the guarantee that it will always find globally optimal solution is, there is a mathematical proof which says that for an LP, the optima in this case is here, 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 or here. The optima occurs at the vertices. So when you have a linear programming problem, I can draw these lines. Show you this. Okay. So each of this constraint has been plotted. So x2 less than equal to 5. So I have drawn this line, x2 is equal to 5, and anything below x2 equal to 5, because the constraint is x2 less than equal to 5. So all these are feasible region for this constraint, x2 equal to 5. Similarly, I can plot all my constraints, right? And in this case, the place wherein all the constraints are satisfied, that is the shaded region, which is feasible. So for an LP, there is a proof that the optima, the globally optimal solution, occurs only at the vertices. Right? So a very famous algorithm is simplex algorithm. So for solving a linear programming problem, broadly two types of algorithms are used. One is simplex algorithm and another one is interior point algorithm. So what the simplex algorithm does is, it starts from a vertex, it moves, keeps moving to next vertex. So when I say next vertex, it is not the neighboring vertex, but a better vertices, right? So if I am here, the objective function, if it is less than, let's say the value becomes 5, then I will move the algorithm has a series of steps, which when you implement, you will move to the next vertex, which is better than this, right? And again, remember, I am not visiting all the vertices. If I visit all the vertices, then I don't need optimization. It's more like an enumeration kind of thing. Right? So I do not want to visit all the vertices. I want to start from a particular vertex, and from one iteration to the other iteration, I want to keep moving. Right? And since for this linear programming problem, it is guaranteed that the optimal solution will occur at one of the vertices, there is a guarantee that linear programming problems can be solved to global optimal solution. So again, I have not taught you simplex algorithm. Right? So I'm just saying that there is an algorithm which will guarantee you that whatever you are finding out is the best possible solution. When I say best possible solution, that is globally optimal solution. It is not restricted by my capability. I have that capability to find out whatever is the best in that search space. So this is true only for LP and MILP. It is not true for NLP and MINLP. So is that point clear? Any doubt on that?
No, sir, it's clear.
Okay, fine. Again, a common mistake that people do is, this is a linear programming problem. People will start using meta-heuristic techniques to solve this. Right? So for example, particle swarm optimization, genetic algorithm, they will solve this problem using meta-heuristic techniques, which in some sense is incorrect, right? Because even if TLBO or genetic algorithm is able to give you a globally optimal solution, there is no guarantee that it has found the best possible solution. So when you have linear programming and mixed integer linear programming, the best thing is to resort to a mathematical programming technique. So this is what I have, mathematical programming techniques. So you can get guaranteed optimal solutions not for all optimization problem, for well-structured problem. So linear programming, mixed integer linear programming, quadratic programming. Quadratic programming is when your objective function is a quadratic function. So if this happens, then you should actually use mathematical programming techniques, because it will give you a guaranteed optimal solution. So I am not saying TLB or genetic algorithm cannot solve this problem. What I am saying is it is inefficient to use them to solve this problem, right? Whereas if you have a nonlinear programming problem or a mixed integer nonlinear programming problem, then neither mathematical programming techniques nor meta-heuristic techniques give you guarantee on finding out the optimal solution. So that is why for these type of problems, prefer mathematical programming techniques. So maybe those algorithms might be covered in this FDP. So there you will be able to see that they will explain saying that one run is not sufficient. So usually how we are used to is you have a problem, you solve it once, that is the end of it, right? But meta-heuristic techniques are more like experiments. It is like you never stop with performing one single experiment, because there are many variables which are not under your control. So you will perform 3 or 4 experiments and take the average reading. So meta-heuristic techniques have that problem, right? So for example, they'll say start with a random population. Now my algorithm performance depends upon the random population. I take population A, someone takes population B. Both of us will end up with different solutions. Both of us are doing it correctly, right? But we'll end up with different answers. So this you would have noticed when you are solving nonlinear equations, right? I start with one initial guess, someone starts with another initial guess. Very likely that both of us will reach some different solutions, right? So same thing happens in meta-heuristic techniques, which does not happen over here. So it does not require multiple runs and lower computational resource. So since I do not have to run multiple times, the amount of time that is required to solve the problem is usually lower in mathematical programming techniques. So again, in meta-heuristic techniques, you will see that they will say take a population size of 50, perform 20 iterations. So then your question is, what happens if I take more than 50 and less than 20? They will say yes, your algorithm may give different solutions. So these are parameters which are to be set by the person who is solving the optimization problem, right? And there are no strict guidelines on what should be this, right? So what happens is then you try with different population size, you try with different iterations, and then anyway there is no global guarantee. So because of that, you resort to mathematical programming techniques. So there are no parameters in mathematical programming techniques which are to be tuned by trial and error. So this is particularly true for simplex method and branch and bound method. So this is for LP and this is for MILP. Right? So those are the advantages of mathematical programming techniques. The drawbacks is that my problem has to be of this form: minimize f of x. Right? F of x is is a function of the decision variable subject to g of x less than equal to 0, h of x equal to 0. So this is to represent all inequality constraints. This is to represent all equality constraints. Right? So x1 square plus x2 square should be equal to x3 square. So this is represented by this constraint. I will bring x3 square to the left hand side and my right hand side is 0. So my optimization problem has to be expressed in this canonical form. This is called as canonical form, right? And very often you don't get this, right? This is something that you, from a problem description, you will have to first formulate the problem. So I don't know how much time I am left with, but if I have 10-15 minutes, I will show you one problem, which is actually an MILP problem. But by the time I finish describing the problem, it is not like you will directly get this. Only in textbooks, textbooks as in like textbooks which are oriented towards demonstrating techniques, right? There are two types of textbooks in optimization. The most relevant, the most popular ones are those which actually show how to solve a given problem. So they will start with this, that your problem has been given with this. They do not talk much about modeling. But what is important is the modeling also. because the technique ultimately it goes into some software. You use software knowing a little bit about the technique, or maybe in some cases not completely knowing anything about the technique. Because you have an Excel solver, you will dump values and it will give you. But this formulation is something that at least now you can go back to ChatGPT and ask for this problem description, give me a mathematical programming formulation. It will give with a lot of errors, but at least there is some help now. But previously it is something that you are supposed to do. So I have a problem description. From there, I formulate a problem and reach a model, and then this model has to be solved to get my solution. Right. So this model is what is problematic in mathematical programming techniques. This is the crucial step, that you should be good in formulating the problem. And if you are able to formulate your problem in this sense, then you will be able to solve it to global optimality. So that is a drawback of mathematical programming technique, whereas genetic algorithm, TLBO, do not require it in this form. Right. So if you want a if condition, so for example here in English, as per natural language understanding, this is a valid constraint. If x is equal to 2 implies y should be equal to 3z. So is this a constraint? Yes, this is a constraint, that if x is equal to 2, y is equal to 3z, and x, y, z, all three are my decision variables. Right. This is my constraint, that if x takes 2, then y has to take 3 times z. Now this constraint is not of any of these two forms. So here what is allowed is g of x less than equal to 0, h of x is equal to 0. So this if condition, I need to get rid of this if, and this implication, I need to do something to this constraint so that I end up with this. So it is doable, right? People have worked on it. These are standard ways to do it, but it requires a little bit of expertise in modeling. There are two expertise which are needed. One is given a model, how to solve, right? The other one is given a problem description. When I say given a problem description, in plain English or plain natural language, the problem is expressed. From there, you need to formulate it such that you get into this mathematical model. So any doubt on this? Fine. So I think so they will share the slides. I'll share with the organizers. They will share the slides. I think so sometime down the week I have one more lecture. So please go through these slides, and at least the slides which I'm covering. There are a lot of slides. No, I'm not covering all of the slides, but whatever slides I'm covering, please go through it. And if you have some doubts, we can handle it in that session also. So that session, probably first 10-15 minutes, we'll have for doubt clearing of whatever you doubts you have over here. Okay, so some of this I'm not doing because that is something that you would have done. So for example, if where do I have that? Okay, don't think so I have it here. So if you do not have a doubt, I can discuss a case study with you.
Sir, I wanted to ask you one question. Hello?
Yes, ma'am, please tell.
Sir, I wanted to reduce the traveling time, like traveling conjunction time. So I just try to work on this. So I choose the different time slots with different segments, and which algorithm is appropriate for this. I try with genetic algorithm, but I'm not reaching the the final answer.
Okay. So you can, I think so the organizers might teach you TLBO. You can try with TLBO, and there are, if you are solving a problem with genetic algorithm, then at least there are 5 to 10 other techniques which you can directly apply. Okay, so just to let you know, I can understand Tamil. As the organizers read out, I am basically from Pondicherry. Right? So if you are talking in Tamil, be a little bit careful. Okay, so the question was that conjunction problem. So genetic algorithm is not giving you a solution. That was ma'am's
Yes.
question. So you can try couple of other algorithms, TLBO, PSO. Very likely that they might give you a solution. Or else I completely do not understand that conjunction time traveling problem, so I cannot comment much. But if you are able to formulate it as an LP or MILP, it is going to be initially difficult if you have not worked in the field. But if you are able to put it as a LP or an MILP, I would suggest that you can look into that. Right? Then you have standard solvers, just like you are using a Python library or a MATLAB inbuilt function for genetic algorithm. For linear programming and mixed integer linear programming also, you have standard libraries. You don't need to learn simplex algorithm to use it.
Okay. But
So
sir, I'm not a formulate as a LP because I'm taking the different time slot like 9:30 to 10, then 10:30 to 11, like this only after 30
so
minutes
even in those
durations.
cases,
Huh?
so whatever is your problem,
Yeah,
you
yeah.
put that problem, like do a search with respect to mathematical programming techniques. Right?
Okay.
Then there might be a formulation in literature. So what you are telling is what is a standard problem in chemical engineering or most process industries, that I have 5 different machines. Which machine do I assign to process at what time?
Okay.
Right?
Okay.
So I have seen reasonable number of MILP formulations for that. Some of those formulations may be directly applicable, or you might have to tweak around those formulations.
Can you suggest me one to name, sir?
Sir,
Yes, ma'am.
excuse
Just
me.
drop a
If you can go in for the case studies, everyone can learn, sir. This both of you are talking, which will not
yeah,
be
yeah.
helpful
So
for others because we don't know what the problem is. Even
correct.
that madam's
Just one.
problem.
That is why, ma'am. Just give me 1 minute. So
This is a common forum, so if you can go to this case study, then it would be good, sir.
yeah. So this what I'm telling is not only for that person. It is true for everyone. So if you have a specific query, you can just drop an email to me. I'll get back to you on that. Okay. So this is a. So some of you need to mute your mics. Okay. Thank you. So this is a production planning problem. So in this problem, what I have is uh, I have a set of products. So product T1, T2, T3, T4, T5, and so on. Right. So there are like this 24 products. So 24 products, and some of these products can be produced by multiple processes. So this is my product T20. This can be produced by let's say process 44, 45, 46, 47. This is to remove any engineering biases, any particular field. I have called it as T and P, but all of these are practical problems. This is taken from a journal article, Engineering Optimization. So those products and processes are real life processes and real life products. Okay. So here, what I have is that this particular process, right? So what I need to decide is I have money, right? Again, I have plain land. I have not installed anything. So what I am first deciding is what are the processes which I should use, right? It is not like these processes have already installed and I need to decide. I have only barren land and I need to decide which are the processes that I want to use, and I will install those processes only. So for each of this process, I have
Sir, not audible.
Please turn on your mic, sir.
Sir, your microphone is off, sir. Hello, sir. Sir, your microphone is off, sir.
Okay, I think so. Someone over there muted me.
Okay,
Fine.
okay, sir. Okay, sir. Maybe I have by mistake because I
Yeah,
was.
I got it. You
Okay,
were
sir.
trying to
Sorry, sir.
mute
Sorry,
everyone
sir.
else. No, no, completely. I can completely understand. In fact, I'm thankful that you muted everyone else.
Because they are disturbing, sir.
Correct. Thank you.
Okay, sir. Okay, sir. Please continue, sir.
So what I was telling is, just to repeat, I have various products that I can produce, right? So for example, in this case, I have T1
Please
to
share the
T.
screen, sir. Screen, please share the screen.
Sure.
Screen not visible, sir.
Thank you, sir. Thank you.
Now it is visible, sir.
So I have these 24 products. I need to decide which of the products to be produced. And it is not sufficient. I decide which of the products do I need to produce. I also need to decide which of the processes should I use. So now the point is, all the processes are not identical. So for example, if I use process 1 and if I produce 70 kgs, right, the cost that I will incur is 50.7 rupees. If I produce 135, the cost that I incur is 90.1. If I produce 270, the cost that I incur is 170.7, which is different from process 1 is different from process 2. All of those three processes produce the same product. Again, remember, what I am doing is, I have plain land, barren land. These processes are not installed, right? I need to decide which of these processes I am going to install, right? So it's not like the process is available, I will use. So right now I have done only a little market survey, and I have said that if I use this particular process, then for producing 70 kgs per year or per hour, I will incur a cost of 50.7 rupees per year or per hour, right? The units, as long as they are consistent, you don't need to worry about the units. And on top of this, I can produce anything above 70, below 270, right? So what I have is, I have L, M, H. In this case, I have 70, 135 and 270. For L, the cost is this one, 50.7. For M, the cost is 90.1. And for H, the cost is 170.7. And between this, I have a linear function. Right. So if I decide to produce anything greater than 70 and less than 135, let us say I decide to produce 90, then the cost is, from this line I need to find out what is the cost. And it's not a same straight line, right? The way I have plotted the points, it might look like it is a same linear line, but no, it is a piecewise function. So for example, this is over here. So it is like this. Right? So if I decide to produce above 135 and below 270, if I decide to produce 200, then I need to use this particular line to find out the cost. So is the problem clear so far? I have
What
a
is
set of
LMH
products.
actually?
Sorry, ma'am.
LMH is actually, what is that? It's three kind of parameters, L, M and H.
LMH is production quantity. How much I can, so if I produce 70 kgs per hour, the cost
Okay.
that I incur is 50.7 rupees per hour.
Okay.
So this is capacity and this is production cost. So production cost includes everything, cost of raw material,
Okay.
cost of electricity, labor, all those things. So I have done a market survey that if I use this equipment, if I buy an equipment which can produce 70 kgs per hour, the periodic cost that I incur is 50.7.
Equipments. So these are different type of equipments, L, J, MJ, and
It's
H.
the same type of equipment. It is the capacity, right?
Oh, okay.
10 passenger car, 10 passenger van, 20 passenger van, 30 passenger bus, something like that.
Okay, sir.
Any further doubt in this so far? Okay.
Out of this three, when we see that itself, we can say that the P1 is minimum. Then what about the P2 and P3, sir? There are three things: P1, P2, P3. In
Correct.
P1, everything is minimum. So we will choose only that one.
Correct. Very good point. Right. It also has something called as investment cost. Right. So production cost is every time I need to do it. So for example, if I produce 50 kgs per hour, then my 50.7 kgs has to be spent every time. Right. So this is production cost, regular occurring cost. And then I have investment cost. Investment cost is one-time cost. So investment cost here, if I see, if I put a plant of L capacity, then the cost is 55, right? One-time investment cost. Here is 81.1. Here it is 131.6. So I have an investment cost. I have a production cost. So in case if you are able to completely decide that process 1 is inferior to process 2, then you can remove process 1 from this entire table, right? But you will not be able to do it with respect to every criteria. So now I had production cost. On top of that, I am putting investment cost. On top of this, I will also put a raw material cost. So basically, I have this figure. So given any process, I have LMH, right? And remember, I have the freedom not to produce also. It is not mandatory that I need to produce every product, and it is not mandatory that I need to produce every process. So this star blinking over here, that is also a valid value for the decision variable. So my decision variable is how much do I produce, X. So now X can take 0. 0 is perfectly possible, and X can take any value between L and H. So this is an example of semi-continuous variable. It has a value at 0. Greater than 0 and less than L, it is not permissible. So there is a hole, which at least in production planning problem, I call it as domain hole. So I have a domain which is 0 to H, but in between I have a hole, which is not permissible. What is that hole? Greater than 0 and less than L. So this line A is for the production cost between L and M. Line B is the production cost between M and H. Similarly, I have line C and D. This is for investment cost. It is with respect to again with LM and H. So this is the problem so far, right? And I do not have infinite amount of money to put all the processes, right? So one thing which Madam correctly pointed out is that process 1 seems to be cheaper than process 2, right? But if I use process 1, then I am limited by this capacity that I can produce at the maximum 270 only. Whereas process 2 gives me the flexibility to go all the way up to 300. Process 3 gives me the flexibility to go all the way up to 310. So obviously you can say that why do you use P1 and P2? Use P3, right? That is true if there is a definite guarantee that I have to produce T1 and I also need to produce up to 310. Right. So for example, I have budget only for producing 200, let us say. Then I might use process 1. So that way I cannot remove process 1 before starting the optimization problem. Process 1 has a drawback, agreed. But process 2 and process 3 have a drawback that their costs are high. Right. So here if you see 56.8, 56.9. But again for different production, it is not for the same production. So this is not cost. The cost is over here, right? But a drawback of process 1, let's say process 1 was cheaper. So the drawback of process 1 is that it can produce at the maximum only 270. So that is what makes optimization interesting as well as meaningful. So you might have three variables. You would know that variable 1 impacts your objective function in this way, variable 2 impacts in the other way, variable 3 in some other way. But all these three variables put together, how does it impact your objective function? That is very often it is not clear from the physics of the problem. So that's why you say that I know that if I work hard, I'll be better in my life. Agreed. So that is one parameter. But then you have 3 or 4 other parameters whose impact together simultaneously you do not know how it is on your objective function. That is why you solve optimization problem. And that is why just from the physics of the problem, it is not possible to say that this is the best one. Is it okay so far? I just need 10 more minutes. After that, I'll wind it up. Any constraints so far?
Sir, thank you for such nice clarification, sir. Sir, actually, I'm not sure whether it is correct or not. So most of the papers are now we're finding that works on this NGable method. So is it in the same, sir, when we are combining more than one methods to get the better solution, better accuracy?
What we are discussing is not in that context, but in symbol optimization, I understand that first you run one technique and you take the result of that technique and put in another technique and do it. That's what you're saying, right?
Yes, yes, sir.
I mean, particularly in literature, people do fancy things, but are they really required or not? Only the person who is working on the problem would be able to do. And that's not a big deal. If I have two other algorithms, the second algorithm, I can always start from the result of the first algorithm. Right? In fact, first algorithm itself, if you twin the parameters properly, that first algorithm itself might take you to a particular solution.
So actually, I have no idea, but I found this concept most of the authors they're using now. And that's why I had a doubt. That's why I asked.
No, that is true. And I'm glad that you asked. I should have ideally covered that in the introduction to optimization itself, that combining 2 or 3 different techniques is also a popular method of solving a particular problem.
Okay, sir. Okay, sir.
Fine. So on top of this, I have raw materials which are required. So if I have to produce 1 kg of T1, then I require this much amount of raw material 1. Right here, this much amount of raw material 1, this much amount of raw material 1 over here. Their cost is accounted over here in capacity, right? So I don't need to separately worry about cost of raw material. That is taken care, because here I am saying if I produce 70 kgs, I require 50.7 rupees. So it takes into account all the cost, but this tells quantity, right? So if some raw material is available in limited quantity, even though the profit from T1 may be very, very high, I may not be able to produce a lot of T1 if that raw material is not available in plenty of quantity, right? So there are 3 raw materials in this example. So raw material 1, then you have raw material 2, and then you have raw material 3. And then I have over here on the left hand side, I have this cost, selling price, right? So this is my cost and this is my revenue. So for 1 kg of T1, how much money will I make? So 0.975 is my revenue. So from there, I need to subtract my production cost. So production cost is not directly 50.7. It is 50.7 for 70 kgs, right? So, but this 0.975 is for 1 unit, for 1 kg of the product. So here at the top, if you see, this is monetary unit per unit of product. This is units of product per year. So this I need to multiply by how much I am selling. So 0.975, and if I produce 130 kgs, then I need to multiply 0.975 into 130 minus what is the production cost. So that is my profit from that particular process. So my objective is to maximize the overall profit. And I have constraints on my budget that I do not have a lot of money. I have a given amount, right? Let's say 1,000 rupees or 1 million rupees or 1 billion rupees. So whatever investment plant I need to set up has to be less than that. And raw material is also not available in abundant. I have limited amount of raw material. So raw material 1, I have only 500 kg. Raw material 2, I have 800 kg. Now, given these constraints, I want to maximize my profit. So many of you would be, which is extremely good, you will be thinking on how will I solve the process. But my objective is what was not to help you solve the process, solve the problem. That requires an entire 2-hour lecture. What I want you to just understand now is what is an actual optimization problem, right? So this is how the optimization problem will be given to you. It is not like maximize x1 square plus x2 square subject to x2 less than equal to 3. So those equations would not be given. What you would be given is description of the problem. So these 2 slides, this is, just this slide is the optimization problem. What you have in the next 3 slides is a case study, right? If you want to solve this, you need a case study. So you have a case study for that. But this is the problem description. So this is what ideally you will have in real life when you are trying to solve an optimization problem. From here, you need to formulate the problem. You need to come up with a scheme as to it is compatible either with mathematical programming techniques or with respect to meta-heuristic techniques. So that is the first step. Once you get that step done, the second step is easier because you have solvers software which is available that will help you to solve, right? But the primary part is this part, which is very often ignored, that all you get is a description of the problem. From there you need to first formulate it, right? So the other problem, again, I understand it's not common to everyone, but still I am referring to the problem because it exactly fits over here. So there they wanted to optimize something, but they do not have a mathematical formulation. The first thing is they need to mathematically formulate it. Once they have formulating it, then solving is straightforward. It is more like using Excel or using your calculator. The entire premise is how do you formulate the problem. Okay, so if you have any doubts, I can take those doubts either today or later. If you are interested, there is an YouTube video also on how to solve this problem, right? If you want to go through the slides, you can go through the slides, or you can go through that YouTube video only if you are interested in how to solve this particular problem. But the objective here was to just give you a feel of how an optimization problem in real life looks like. Any doubt?
What is it, level 1, level 2, like that you're saying it in the box, no, sir? Process 1, for process 1, level 1, level 2, like that you're saying. What is that? Level 1.
Okay.
Sir.
Fine. So I'm just thinking of a best way to explain it. Right now, I'm not getting. So you can think of it as a container, right? So process 1, I can buy any of these 3 containers: 70 kg container, 135 kg container, and 270 container, right? If I buy 70 kg container, that container I can use to produce all the way up to 135, right? So it is more of the size of the equipment. So size of the equipment between 70 to 270, there are infinite points. I do not have values for all the points. So what I am saying is between 70 to 135, the cost varies linearly from 50.7 to 90.1. Between 135 to 270, the cost varies linearly between 90.1 and 170.7. So it is like how much do you produce, right? How many people do I take, right? Do I take 70 people or 135 people or 270 people? Those are the capacity of the vehicles I can buy. But if I buy a 70, that 70 carrying capacity can also be stretched all the way up to 135. So the one that I am buying for 135 can be stretched to all the way up to 270, because it's a continuous between 70 to 135. That is why I'm saying that you can stretch that capacity. So for example, let's say I have a process 1, let us say I have selected, right? So when I say I have selected process 1, what capacity of the equipment should I put? That is in my control, right? I can put anywhere between 70 to 270. The minimum container size is 70 and the maximum container size is 270. So between 70 and 270, I can put any container size. Is it slightly clearer than what you were when you asked that question?
Sir, in this only three things are there: 70, 135, or 270. But in the process, what you are saying, some level 1 to level 5. So that how to
Oh,
correlate
okay,
this?
okay. I got your confusion. So this one, right? This
Yes,
is a
sir. In
generic case.
process one, yes,
That is
level 1, level 2.
that is what I'm saying. So this is a generic case that you don't need to have same levels. So in this case, you have M, H. So this L2 is nothing but M. This L3 is nothing but H. Right. So like that, you have various levels in first process. In second process, you don't need to have the same number of levels. I have only 2 levels. So this is a very generic problem. This is a particular case study. In this case study, the number of levels are uniform. In all of the cases, it is 3. Right? But you can vary this also. So in process 1, you can have only 3 levels. In process 2, you can have 5 levels. That is the information which is available. So for process 2, someone is willing to manufacture at 75, 150, 300, 500, and 1000. So in that case, for process 2, I will have 5 levels. So if you are trying to correlate with case 1, this slide and the second slide, this slide is a very generic slide. Right? That second
Okay.
slide is a specific example in which all the processes have three levels.
Okay, okay, sir. Okay. Thank you.
Fine. So if there are no more questions, I think so. I had
Sir,
time from.
in your slides itself, you have shown how to solve this problem. Is it, sir?
Yeah, yeah.
How to
So,
solve this problem, or you will give that video link so that we will be able to see that.
so you can see the video link, or else what I would suggest. I mean, if let me see if I can spend 5 minutes. So this is a problem which can be solved by both methods. The first method is what we show meta-heuristic techniques, and the second one is an MILP formulation for the same. Right. So both of the methods are solved for the same problem, and this particular slide shows that. So if I take a mathematical programming approach, so whatever problem description I gave ultimately can be boiled down to this left hand side, the mathematical programming. So this formulation, if you see, I have integer variables. So y and z can take either 0 or 1, not any value between 0 or 1, either 0 or 1. So that is y and z. And then I have continuous variable xl, mh, which are greater than 0, which means they are positive variables. And I'm not going line by line, but take it from me that all of these constraints are linear. This is not nonlinear. IL into L is not nonlinear because IL is known to me, right? What is not known is L. So that is the decision variable. So all of these constraints are linear, and I have continuous variable as well as binary variable. Binary variables are subset of integer variable. So this is a mathematical programming, and in that it is a mixed integer linear programming for MILP. So that was the problem description which I gave, right? And if I formulate it, I end up with this mathematical programming formulation, which happens to be an MILP. So I did not start saying that I will make an MILP formulation. Whatever was required to capture the problem dynamics, I started capturing it, and I ended up with an MILP. If it was in my control, I would have stopped at LP. But LP I cannot stop because you have discrete nature, right? Between L and M and H, then 0 is over here. So there is discontinuity. So it ends up with an MILP approach. So that is on the left hand side, right? Same thing here, they might teach you TLBO and other meta-heuristic technique. If I were to use meta-heuristic technique, I will not use the left hand side. I'll use the right hand side. So here what I'm saying is it will give me a solution. I will see if the solution satisfies the constraint, and if it satisfies the constraint, I will calculate the objective function. If it does not satisfy the constraint, I will add penalty and calculate fitness function. So same problem can be solved can be modeled in two different ways. This is one way for mathematical programming techniques. This is another way for meta-heuristic techniques. So this particular presentation contains both, that I take a problem and I try to model it for meta-heuristic technique. I try to model it for mathematical programming. Mathematical programming, at least in my perspective, right, is little bit difficult, but then it is worth doing it because the left-hand side formulation is difficult to arrive at. The right-hand side formulation is extremely easy to arrive at. But the left-hand side formulation, if I solve, I will get a solution which is guaranteed that this is the best possible solution. There is no other better solution than that. That is in left-hand side. Right-hand side, easy to arrive at this, but when I finish solving it, I will not be able to give you the guarantee that this is the best possible solution. There is no better possible solution than this. That guarantee I will not be able to give it in the right-hand side. So that was the premise of taking this case study, not for you. For this particular lecture, the premise was just to show you actual optimization problem, because very often what we end up doing while teaching something is give the problem directly. But many times from the English language or the language description of the problem to the mathematical form, that is what is critical. So once you get that, then that can be done in two ways.
Sir, one thing from you said that problem we are able to know completely that case study. From that, how did you bring these equations? How to write the equations for that problem? This is the equation for that problem. How to write these equations? If you can say something, then we will be happy, sir, because we will learn a lot. I hope so.
Correct. So that I need another 1 hour, at least 1 to 2 hours for explaining this equation. Forget how did I come up with it. What these equations mean, that itself will take an hour. So there are standard books which are
What this
available.
equation means, we are able to know, sir. The only thing is how to, you said that problem. For that problem, you have framed these equations. How to do that alone, if you say, then for any other problem, we will also be able to do
Correct. I
some
completely agree. It's just that what I'm trying to say is that is what is important. That is why I brought in this aspect itself, right? But for that, I cannot do it in 5 minutes. I need a reasonably good amount of time to explain this. So for example, I can, if you want me to give a hand waving argument, I will say IC indicates the investment cost. So this constraint would be straightforward. The one that I'm highlighting, this would be straightforward. Sorry. This would be straightforward. IC is the investment cost for every process. So I am summing across all the process, and that should be less than.
Screen is not visible, sir.
I think stop the screen, sir. Please share again. Yes, sir. It's working, sir. Thank you so much.
Now it is visible, sir. Now it is visible.
Okay. So for example, this particular constraint, IC J. So J is for the jth process. So I am summing across all the process, the investment cost, and it should be less than equal to budget. So that is this constraint. This IC J is less than equal to B. And what I am saying is, you saw those three levels, right? L, M, H. So I am saying this capital L, capital M, capital H is the fraction that I am producing from low level, fraction that I am producing from medium level, and fraction that I am producing from high level. That I am multiplying with its capacity. So over here, if you see, investment cost is IL, IM, IH, which is given to me. So IL is a single variable. It is not I into L. IL is a single variable. So that value is known to me. And then I am saying what fraction I am producing from low level, what fraction I am producing from medium level, what fraction I am producing from high level. These three things put together, I am calculating my investment cost. Right? And this constraint, if you see, L plus M plus H, right? So that has to be equal to 1. So low level plus medium level plus high level should be equal to 1. But I can use either LM line or MH line. I cannot use both the lines. So I can produce, if it is 50, 135, 200, I can produce between 50 and 135 and between 135 and 200. I cannot produce something between 50 and 135 and also between 135 and 200. So what I am ensuring is either LJ will be active or HJ will be active. Only one of this will be active. So Yj is a binary variable. So if it takes 0, then Lj is 0, because Lj is a positive variable and I am saying Lj is less than equal to 0. So Lj will become 0 and Hj will be less than equal to 1.
Again, your screen is not visible.
Not
Screen
doing
has gone.
anything at all. Just 1 second.
Just stop, sir. Just please share again.
Okay. So what I am saying is I will use 3 variables, capital L, capital M, capital H, whose values I don't know. I want to decide. But I want either L and M to be active or M and H to be active, because if you see those lines, I have 2 lines, right? Between L and M, 1 line, between M and H, 1 line. So what I am saying is I will use a binary variable, Yj, to indicate whether I am in the first line, that is between L and M, or whether I will be in the second line between M and H. Right? So that is indicated by Yj. And then I am saying I will use a variable Zj, which will decide whether I am producing or not, because I also have the problem, that freedom. The problem becomes complex only because I have that freedom, that I can choose not to produce. So what I am saying is Zj, if it takes 0, it has the freedom to take anything, 0 or 1. If it takes 0, then L, M, H, they will go to 0. And X, if you see, it is dependent on capital L, capital M, capital H. So X will go to 0. So if X goes to 0, the revenue I will get goes to 0. And my production cost will also be 0, because capital L, capital M, capital H is equal to 0. So when I don't produce anything, that is captured by Zj, right? So Zj is going to be a variable. So when you ask that how will I go about getting this equation, so first thing is I will say that let me have a binary variable Z. That variable should take a value of 1 if I am producing. That variable should have a value of 0 if I am not producing. So first in my mind, what variable will come is Z variable. Then in my mind, I have to decide that whether I am between Y and M or am I between M and H. So I need a binary variable, either first line or the second line. So that I am doing with respect to Y. Right? That's how I end up with this equations. This equation is relatively straightforward, the raw material equation. So Rm is a single variable, right? It is not R dot M. It is Rm single variable. I know for the jth process, the kth type of raw material, how much is required, that is known, right? And how much I am going to produce will be known, that is Xj. So I am multiplying that and across all the processes. So process 1 requires raw material 1, process 2 requires raw material 1. So like this, I am adding all the processes. So that's why I have this summation symbol. So for individual process, I calculate and I add through all the processes. So that amount should be less than equal to what I am having. So capital R is the variable and small k tells me which type of raw material. First raw material, second raw material, third raw material. How much I have, that is known to me. R suffix k is known to me. And this is what it will be required. So this is how I will kind of formulate those equations. Again, I myself can tell you that I have not explained it to 100% of my own satisfaction, right? Usually our satisfaction, the person who is giving the lecture reaches the satisfaction first, and then those who are following will reach the satisfaction. So I myself am not satisfied 100% because I need time, right? I have to go through all these slides. So from slide number 44 onwards, it captures all of this. Right? It discusses all of those cases, that if this variable happens to 0, what happens to my equation? If that variable happens to be 0, what happens to my equation? And then I end up with slide 63, the first half of slide 63. So what is probably a 35-40 minute lecture, I tried to explain it in 4-5 minutes. So I myself am not satisfied. So obviously I can expect that many of you may not have been able to completely grasp it, but it is just to give you a hint that I need a decision whether I am producing or not. So I take my first variable Z. Then I need to decide whether it is between L and M or M and H. So I have my another variable Y and so on. So again, if you are interested, there is a YouTube lecture for this also, just explaining this formulation. You can have a look at it.
Sir, please share that YouTube video link and your NPTEL title, sir.
Sure, sure.
And one more request, sir. So after solving all these equations, you said that through the solver you can solve those equations.
Hmm.
Can you solve the same equation through the Python programming, sir? Okay, sir.
So Python programming, Python, MATLAB, all of those are programming languages. So what I am telling is techniques. So those techniques are available for all languages. So you can solve using those.
Okay, sir.
Any other questions? I'm sorry I took a lot of time. I am supposed to wind up at 8, but it's almost 8:30. I came obviously 15 minutes late, 10 to 15 minutes late. So if there are no more questions, I will thank you all for patiently listening. And more importantly, special thanks to all of those who asked questions.
Thank you, sir. Thank you very much. It was very clear, in spite of your everything in the beginning.
Thank you, sir.
Thank you, ma'am.
Thank you.
Thank you, sir. A small request. So,
Sure.
could you please give us more sessions on this in future nearby?
Sure.
Thank you, sir. Thank you for the beautiful analogy. That was really nice.
Thank you. Thank you very much.
कंप्यूटर का नाम है
Sir, can you please share your email address so that we can send some queries to you in person?
Sir, can
You
you
can
share the
check in the program schedule. I think SAR's email ID is there in the program schedule.
Okay, ma'am. Thank you, sir.
All the speakers, right? Email IDs are there in the program schedule.
Thank you, ma'am.
Ma'am, can we have the PPT?
Yeah, it depends upon the right resource person. If they will share, we'll give, because all our NPTEL courses are is telling, right? So it is available. We can check it.
Or can we have the recording session, ma'am?
A recording session will give.
Okay, ma'am. Thank you. Ma'am, today is stopping or still lecture is there, ma'am?
Just 1 minute. Let me give 1 minute. I will inform.
Okay.
Yes, sir will join after 5 minutes, 5 to 10 minutes. After that, sir will continue for another half an hour. Please wait for 5 to 10 minutes.
Okay, ma'am.
Okay, okay, okay.
Can we start, madam?
Yes, sir. Yes, sir. You can start, sir.
Thank you. So sorry to everyone. I thought it was till 8:30. Later realized 9:30. The organizers meticulously sent me multiple emails. It was my mistake. I didn't see it properly.
No problem, sir. No problem, sir. It may happen, sir.
Okay. So I understand now this lecture is not as popular as it used to be before Python was in the scene. Now many of you would have preferred if we had done this in Python rather than in MATLAB. But MATLAB has its own advantage, and I have not prepared for Python. So we'll keep this session primarily with respect to MATLAB. So there are some inbuilt functions. So here our objective is to see as many functions as possible, as long as I can keep you interested. So linprog, it's for linear programming problem. So here
Sir, whether you have shared PPT, sir?
It's not visible today.
No, sir, it is not visible.
Today my day is very bad.
It is not visible, sir.
Just 1 second. Usually I don't mess up this much, but today it has been little. So is it visible now, ma'am?
Yes, sir. Yes, sir.
Okay.
Yes, sir, it is visible.
So we'll see as to how many functions we can see. So this linprog is an inbuilt function. So what you are seeing over here is all in this column, the first column, all are inbuilt functions. So this is true with respect to MATLAB 2019, right? So this was what, when we prepared that NPTEL course, it's slide prepared at that time. More or less things have remained the same except for a couple of places that I will let you know as we go along. So linprog is for solving linear programming problem, and int linprog is for solving mixed integer linear programming problem. So first we will get going with these two functions. Once we are done with these functions, then we will jump to fmincon, and then if time permits, we will come to these, right? So if we are able to do this, then we know how to solve a linear programming problem, a mixed integer linear programming problem, and a nonlinear programming problem. And at the end, if time permits, we will look into GA, which is the only function in MATLAB that can help you to solve a MINLP problem. Right. So as we discussed, just recollecting whatever we have done. So in a linear programming problem, the objective function is linear. The constraints are linear, right? So you can have equality constraints as well as inequality constraints. And then I can have bound constraints. Bound constraints are something like this: x is less than equal to x is between 5 and 10. So this is lower bound. This is upper bound. So what these slides, what they discuss is the context of the problem. How did I arrive at the equation? Right now we are not looking into that. Right. So right now what I'm interested in solving this problem. This is the problem that is given to me. Right. Minimize 15x1 plus 10x2 plus 20x3. So x1, x2, x3 are the decision variables, and they are positive decision variables. x1, x2, x3 greater than or equal to 0, and their upper bound is infinity. They will not take infinity because of the constraints, right? But as such, there is no upper bound which is given. And I have constraints which says 0.1 x1 plus 0.2 x2 plus 0.4 x3 should be greater than or equal to 30. 0.45 x1 plus 0.25 x2 plus 0.3 x3 should be greater than or equal to 40. So this is what is a linear programming problem that I have. Now let me see how MATLAB wants me to be, wants the function to be, right? So the linprog requires the first coefficient is z, right? So z stands for the coefficient of the objective function. So in this case, it is 15, 10, and 20. So 15, 10, and 20. I don't need to write 15x1 plus 10x2 plus 20x3, right? So things when it is linear, then the coefficients itself are sufficient. And if let's say for some reason 10x2 was not there, the objective function was 15x1 plus 0x2 plus 20x3. In that case, I need to put 0 explicitly. So all coefficients appear in the objective function as well as in the constraints. On pen and paper, when you are writing, if something is a 0 coefficient, you would not write that variable. So we are not used to writing 0x2. But in MATLAB, I still need to give that coefficient 0. So here I have fixed my ordering that the first variable is going to be x1, the second variable is going to be x2, the third variable is going to be x3. This is something that I have chosen. You can do it x3, x2, x1, completely fine, but you need to be consistent throughout. So I am going with this typical convention x1, x2, x3. So those coefficients I have written over here, 15, 10 and 20. And then I have two constraints. So MATLAB allows only these type of constraints, ax less than equal to b. It does not allow greater than or equal to. So because of that reason, this first constraint I am taking and I am multiplying by a minus sign to get this constraint, right? And then I am writing its coefficient. So the first constraint is first row. So minus 0.1, minus 0.2, minus 0.4, minus 0.4. That is my A matrix first row. A matrix second row is minus 4.45, minus 0.25, minus 3. So this is my second row. And B. So A is to be given, B is to be given. So here A and B, this both have to be given. So in this case, A I have defined, right? And then B is minus 30, minus 40. How do I know that? If I look at the help of LinProg, they would have given this thing, that LinProg solves such problem, minimize F transpose X subject to these constraints. And all of the parameters are to be given like this. First, the coefficients, then the inequality constraint coefficient matrix, then the inequality constraint right hand side, then equality constraint. In our case, for the first example, I don't have equality constraint. Both of my constraints are inequality constraint. So if I had, I will give that. Otherwise, I will give empty brackets. And then I need to define lower bound, upper bound. And if then required, I have to define options, right? So by default, MATLAB has set all the options for us. But if we want to override that, so for example, by default, it might be solving with simplex method. If I want to solve it using interior point method, then I can do it, right? So that's when I will use my options. Otherwise, I will use without options. So if you are comfortable with MATLAB, then this slide will be very easy. Otherwise, I'll explain as much as possible. And then if you have doubt, we can get it sorted. Right? So CLC is a command to clear the screen. Right? In MATLAB, you have command window. So the CLC helps you clear the screen. Clear will clear the memory of MATLAB. So workspace, MATLAB has something called as workspace. That's where all the variables get defined, right? So when you give this command clear, everything in the workspace would be removed, right? So I am cleaning my window, CLC. I am clearing my memory with clear. And then I am defining my lower bound, LB, right? LB I have chosen because it is lower bound, but I can as well say this as cat. It is just a name of a variable. As long as I use this cat wherever LB I have used, I am fine. I don't need to worry about it. So let's go with LB. LB is equal to zeros. MATLAB has an inbuilt function called as zeros. So I don't need to write 0, 0, 0 10 times if I want 10 zeros, right? I can say zeros, 1 row, 10 columns. So in this case, I have 3 columns. So 1 row, 3 columns. So I am saying give me a matrix, a vector, zeros with values zeros. The vector should be a row vector, 1 row, and it should have 3 columns. So that will give me 0, 0, 0 3 times, which is what I wanted in this slide. So this 0, 0, 0. So this percentage symbol is for indicating that whatever appears after the percentage symbol is a comment in MATLAB. So this is not required, right? This is just for my own benefit, that what is that I'm defining in that particular line for my own reference. So MATLAB does not consider this. So this is A, this is B. A and B are whatever we have decoded over here. Minus 0.1, minus 0.2, minus 0.4. Minus 0.1, minus 0.2, minus 0.4. When I want to give the second row, I need to give a semicolon and then minus 0.45, minus 0.25, minus 0.3. So that is my A matrix. Then I have my B vector, 30, 40. B vector has to be a column vector. So it wants 30 and 40. So what I am doing is I am writing it as a row vector, 30, 40. but here I am taking it as a transpose, right? Or if this is confusing, you can directly say minus 30 semicolon 40. So this will define it as a column vector. And then I am defining that variable z, which is corresponding to the coefficients of the objective function 15, 10 and 20. So these are coefficients of my objective function. And then I am calling it over here, my linear programming. So this is an inbuilt function of MATLAB. The ordering is important. So I cannot give a comma b comma z. It will not understand, right? A contains coefficient matrix that is known only to me. For MATLAB, whatever appears second, that is the coefficient matrix. So I need to keep the order. So the order is first is coefficients of the objective function, then the coefficients of the inequality constraints, right hand side of the inequality constraint, coefficients of the equality constraint, right hand side of the equality constraint, which I don't have. So I have given empty bracket, and then I have lower bound. So lower bound is 0, 0, 0 in this case. So this is what is input to the function. So linprog is the name of the function. Input to the function is this. Output from the function is x. So this will tell me what is the value of x1, x2, x3, right? It will give in that order x1, x2, x3, because that is the order in which I have defined everything, x1, x2, x3, and it will give me the value of the objective function, right? So this is what the output would be. So if I type whatever I have in the screen, if I type this is what I will get in the command window, that my decision variables are 7.6923, 146.1538 and 0. So this is my decision variable. The value of the objective function is 1576.9231. So this lambda is something, if you look, I mean, if part of this course or any other course, if you actually do simplex method, then you would know you would come across something called as shadow prices, right? So this lambda is for that. So primarily we are now focused on how to get the values of the decision variable, value of the objective function. Exit flag tells you why did MATLAB stop, right? So sometimes it stops because the number of iterations is reached. Sometimes it stops because the amount of time allocated for that function has been reached. So there are various reasons it stops. So you can look at exit flag and it will tell you why it has stopped. And output contains all this information in one structure, right? X, fval, exit flag, everything in one structure. It is in output, and lambda is the shadow prices. Okay, so this is an example wherein I have equality constraints also. So previously I did not have equality constraints. Here I have equality constraints. So that is one new thing about this example. Other thing is I don't have x2 over here. I don't have x3 over here, right? Still I need to carefully put zeros. Otherwise I will be solving a wrong problem, right? So over here z is 1, 2 and minus 3. The coefficient are z1, 2, minus 3. Here it is, both of them are already in less than equal to form. So I don't need to multiply by minus sign and convert into less than equal to, which we did in the previous problem. So here coefficient of x1 is 1, coefficient of x2 is 2 and no x3. So 0. So here no x1. So 0, x2 1, x3 1. The right hand sides are 3 and 2. So 3 and 2. And then I have an equality constraint in which all the variables appear. x1, x2, x3 appear with a coefficient of 1. So 1, 1, 1. And b equality is 4. So that is 4. Again, this is name of a variable, right? I can write it as again, let's say cat, and I can use cat wherever I require. So this I can use funny, and then use funny wherever I want it. So rest of the things are
very sorry to interrupt. Is this only for minimization we are looking into?
Correct.
Thank you.
So if you know MATLAB, then what I have written here is straightforward. It is just that this information I need to give it in MATLAB's language, right? So z is equal to 1, 2, minus 3, which is what I had. A 1, 2, 0, 0, 1, 1. So 1 2 0 0 1 1. B is 3 and 2. So semicolon, because it requires as a column vector. A has two rows, right? So B also requires 2 rows. So that's why it is semicolon. Previously I did not give semicolon. I gave 3 space 2, but I had a transpose, right? Now I am not having a transpose. I defined it as a next row, 3 semicolon 2, and A equality AEQ 111, BEQ, again both of these are just name of a decision, name of a variable, 4. So that is because 4 and 111. And then in this particular problem, the lower bounds and upper bounds are given. So the variable x1, x2, x3 have lower bound of 0, minus 1.5, 0, 0, 1.5, 0. Upper bound is 5, 3 and 2. So 5, 3 and 2. So this is my lower bound and this is my upper bound. So I define all the variables which are required, and then I am calling this function linprog. Again, remember the ordering is important, right? As with all softwares, you don't need to remember the ordering. You can always say help linprog and it will tell you which is the first argument, which is the second argument, which is the third argument. So since I have used it multiple times, I kind of remember it. Coefficient of the objective function, coefficient of the inequality constraint. So first inequality constraints are done. First thing is within inequality constraint, first is coefficient matrix, then the right hand side vector. Similarly for equality constraint, lower bound, upper bound. For this particular problem, I don't want to change any options. I want to solve with the default options. So just lower bound and upper bound. So if I solve this, I would get this. And remember, you need to be consistent with respect to the notations. So here I have assumed the ordering of the variable to be x1, x2, x3. So this constraint is also 1x1 plus 2x2 plus 0x3. 0x1 plus 1x2 plus 1x3. So that ordering is very important. So if the ordering is consistent, the result which you are getting will be in the same order which I had followed. So I had followed x1, x2, x3. So x1 is going to be 3.5, x2 is going to be minus 1.5, and x3 is 2. Right? And f12 is my objective function value. So at this x1, x2, x3, the objective function value is minus 5.5. So linprog, we have done two examples. One is without equality constraints, another one is with equality constraint. In the first problem, all the variables appeared everywhere, right? In the objective function as well as in the constraints. In the second example, some of the variables were not appearing in some places. So x1 was not appearing in one constraint. In one constraint, x3 was not appearing. So you need to be careful and include this 0 accordingly. Right? And the usual mistake is over here. We tend to write 3 space 2, right? Then it is a row vector, whereas it is expecting a column vector over there. So with respect to the question that Madam asked, it is I mean, MATLAB is used to solving, I mean, can solve only it can solve only minimize C transpose X or F transpose X, right? C is the coefficient, right? So C, I will write it as 185, 189, let us say, and X is X1, X2, X3. So my objective function is X1 plus 8X2 plus 9X3. So this is the syntax in which MATLAB works, minimize C transpose X. Now if I had a problem which is a maximization problem, let us say I want to maximize 8x1 plus 12x2, right? So then what I will do is I will convert this to a minimization problem, right? So now I will say I will go to MATLAB and I will say solve this problem instead of this problem, minus 8x1 minus 12x2 or minus 8x1 plus 12x2, right? So the solution which I get from MATLAB for this is actually the solution for this, right? Why it is? That's the example I gave in that introduction lecture, that if I am minimizing something, then if I maximize the mirror image of that, right? So this point and this point will occur at the same decision variable x. So this is my x and this is f of x, right? So in MATLAB, you will have all the functions only for minimization problem. So if you have a maximization problem, MATLAB expects you to take that first step, that convert your maximization problem into a minimization problem. When I say convert maximization problem into a minimization problem, it is not like I am removing this maximization and putting minimization. What I am doing is I am saying minimize minus 8x1 and minus 12x2. So any doubt with respect to linprog?
So one question, like how about the objective function? We are, for example, let's say like I'm going to maximize certain parameters, and I've got multiple objective function. So
Multiple objective function.
Yeah. Yes, sir. So
Okay.
I'm maximizing some parameters and I'm minimizing some parameters. So for that, when we are in need of MATLAB to be used for doing maximization, we know like we have to do the minus of f of x, whatever you have showed just now. So my question is like, how about does the objective function change as well?
Okay. So linprog particularly is for a single objective function. Right? It is not for multi-objective optimization. Multi-objective optimization, you have two functions. Not sure if I have included over here. Yeah, it's not here. So there are two functions. One is called as Pareto search.
Okay, sir.
And another one is called GA multi-objective, GAMULTI-OBJ. So these two functions can be used for multi-objective optimization problem. And there also they expect the same thing, that both the objective functions are to be minimized. If one of the objective function you want to maximize, then you need to convert negative of that to minimization.
Okay, sir. And one key thing is like, when do we actually devise a fitness function? And what is the key difference between an objective function and a fitness function? Because that clarity, I'm not pretty sure. If it is related, you please answer.
No, that's a very good question. So that primarily comes in meta-heuristic techniques. In meta-heuristic techniques, I have two things. One is objective function and another one is fitness function. Right? In mathematical programming techniques, I only have objective function. So the difference between objective function and fitness function is, fitness is objective function plus lambda times penalty. So objective function, whatever you are having, that will be over here, right? And then I will check. So what happens in meta-heuristic techniques is, the technique will give you a solution. It will not tell that the solution satisfies the constraint. Meta-heuristic techniques are primarily designed for unconstrained optimization problem. So, but you have a constrained optimization problem. So what you do is, the solution which it gives, you take that solution and then you check whether it is satisfying the constraints or not. If it is satisfying the constraints, then you don't assign a penalty. Penalty is 0, which means your fitness function is same as your objective function. But if it is not satisfying the constraint, then you add a penalty saying that you are supposed to have x1 plus x2 should be less than or equal to 10. Now let us say my meta-heuristic technique gave x1 is equal to 5 and x2 is equal to 12. Right? Now 5 plus 12 is not less than or equal to 10. So what I will do is, x1 plus x2, this happens to be 17 in this case. So 17 minus 10, the whole square. So this value, which is 7 square 49, I will add it to my objective function with a lambda.
So the lambda is a smoothing factor.
Smoothing factor, or you are trying to give more importance to penalty than with respect to objective function. So this is equivalent to that example which I said. I can have a student who is scoring 4 into 100 in 4 subjects plus 34. Right? So that student will not qualify when compared to someone who is 5 into 35. Right? So my objective function is important only if it is feasible solution. So I want to place more important on the penalty part. So I am blowing this penalty. It's a scaling factor kind of thing. So what I will have is 10 power 5 or 1000 or something. So that even if I get a small penalty, it is blown up so much that it negates the objective function.
So we have to choose the smoothing factor in such a way that the objective function is of the
Correct. So the objective function should not get importance at all when compared to my penalty. Right. So here, if you see, the violation is just 1. Right, 35 minus 34, just 1. But the fitness of this should be less than fitness of this. So I'll have to multiply that 1 by a significantly large number. Only then that penalty will mean anything.
And choosing the min smoothing factor or max, I'm not sure about the exact term, sorry. Like, for example, when we are having, when we need to have an alarm system, for example, where we have peaks. So that kind of problems we can define the smoothing factor or the lambda. But for our problem statement, we cannot predict like what kind of data can come in. So in case of example for 34, there is only one value that we need not consider. But let's say like we don't know like what kind of data will come in. For example, when we have vehicles to be monitored, I'm going to do for an EV example, I'm going to have when the vehicle needs a charging. So for that case.
Okay, so then in that case, what is difficult in an optimization problem is to find out the best value of the objective function.
Yes, sir.
What is usually easier, not always, usually easier is to find out the worst.
Yes.
Then you can take lambda is nothing but your worst objective function.
Okay, sir.
Okay, fine. So that was linprog. And from linprog to int linprog, it is straightforward. So here I have a problem in which there is a context to this problem that I am not discussing. So let's say I have a problem which when I formulate it, I end up with a integer linear programming. So here x1 and x2 both are supposed to take only integer values. They are not supposed to take continuous values, right? And the nature, I mean, if you look at a LP and an MILP, the structure is same, except for the fact that you need to tell which are the variables which are integer. So in MATLAB, it is exactly same as your linprog, right? But the function is int linprog. First thing is you need to say what are the coefficients of your decision variables. We'll come to this in cont in a minute. Then A, B, which is the same thing. My inequality constraints, what is the coefficient matrix? B is what is the right hand side values. A equality, B equality is for equality constraint. This is for inequality constraint. This is for equality constraint. My lower bound, my upper bound. Initial guess, if I know, I can give that. If I don't know, I can just give an empty bracket. And then options. If I want to change the default options, I can use that. So everything is same except for intcon. So the intcon tells that if I arrange my variables, right? So when you say your z is equal to, so I'm writing a random z before going into that problem. So if I say randomly 5, 8, 9, 7, 3, 30, 16. So it means first decision variable, second decision variable, third decision, fourth, fifth, sixth, seventh. So I have 7 decision variables, x1, x2, x3, x4, x5, x6, x7. And this is the way I am arranging. And if I know, let us say that third variable and seventh variable are integer, other variables are continuous, then intcon, again intcon is just a name of a variable. I can have cat as my variable name. So here I will give 3 and 7. So I just need to say, in addition to everything which I told for linear programming, I need to tell for integer linear programming. In addition to that, I also need to tell which are the variables which are integer. So if only 3 and 7 are integer, you give 3 and 7. If all the 7 variables are integer, you give 1, 2, 3, 4, 5, 6, 7 over here. If the 5th and 7th variable are integer, then you say intcon is equal to 5 and 7. Right? So between linprog and int linprog, only one thing you need to understand: what are the variables which are my integer variables. That has to be explicitly specified. Otherwise it is the same thing. So the problem that I have is maximize z is equal to this, but incline proc solves only minimization problem. So what I'm saying is solve min z minus 5x1 minus 4x2, right? And these two constraints are in the same form, less than equal to, so I don't need to multiply by this minus sign. So those two constraints as such. Here I have a slight problem, as in the right hand side should not have any decision variables, but here I have a decision variable on the right hand side, so I will take it to the left hand side. So minus x1 plus x2 should be less than equal to 1. So after this it is straightforward. The coefficients are minus 5 minus 4, 6 4 1 2 minus 1 1, 6 4 1 2 minus 1 1, 24 6 1, 24 6 1. Only thing I need to be careful is this should be a column vector, and both the variables are positive. Lower bound is 0, so LB is equal to 0 0. Upper bound for x1 is not given, so I am saying INF. INF is an inbuilt MATLAB function, a MATLAB keyword which stands for infinity. So I am giving INF upper bound and 2. So my lower bound is 0 for first variable and upper bound is infinity for first variable. For second variable, lower bound is 0 because of this, and upper bound is 2 because of this. So this would be my code in MATLAB. CLC is to just wipe away my command window with whatever has been printed over there. Clear is to clear my workspace. Z is the variable I am going to use for coefficients. So 5, 4, and both of them are with a minus sign coefficient. So I have put minus outside. A, B, I have 3 constraints separated by a semicolon. Right hand side separated by a semicolon. Lower bound 0 0, upper bound infinity 2, and in this case both my variables need to take integer values. So 1 2. So since it is both variables, it is 1 2. That is why this is a better example. That if I have 7 variables and if I have only my third variable and seventh variable to be integer, then I say int con is 3 and 7, and that is the int con that I am going to use over here. So if I give this, then it will give me the value of x, right? x1 is equal to 4, x2 is equal to 0, and value of the objective function is minus 20. So this is minus 20 with respect to the minimization problem. So with respect to my actual problem, the solution is 4, 0 and plus 20, not minus 20. So whatever my MATLAB gives, I need to multiply by a minus sign only for this fval, not for this x. Right? Because of the same reason that if I have these two, then my minima and maxima occur at the same point. This x is the same. I don't need to multiply by a minus sign. Whereas this is minus 20 now. If I want for my actual problem, this has to be plus 20. Right? So because we converted this maximization to minimization. So any doubt in this? Okay. So again, question is what happened? What would have happened if I have solved the problem using linprog? The second problem, what if I solve using linprog? Then this is the solution you would get. X is equal to 3 and this is 1.5. But if you substitute 3 and 1.5 in your constraints, right, you will 1.5 you cannot even use because the variable need to be integer, but you are getting 1.5 a continuous value. So you would say, okay, I will round it up. Right. So rounding it up, in this case, you can round it up to 2 or you can round it up to 1. Right. If you round it up to 2, you will see that it no longer satisfies the constraints. Right. So, and we have discussed multiple times that my solution can have a bad objective function value, but it has to be feasible. Right. In this case, it is infeasible. Right. And over here, if you consider it as 1, then it is actually giving you a solution which is poor. Right. So the solution which I got from intcon was minus 20 or plus 20 in terms of maximization. Here it gives me 19. Right. So it is a suboptimal solution. So very often this question comes that why can't I solve my problem as a linear programming problem, and whatever decision variables I am getting, why can't I just round it off to the nearest integer? So if you round it off to the nearest integer, two things can happen. One is that you can end up with infeasibility. Second thing is you end up with an suboptimal solution. And in extreme rare cases, you will get the actual solution itself. That is extremely rare. Right? Usually what happens is either the problem becomes infeasible or suboptimal. So for example, you are deciding how many pens to buy. Right? So now you end up with a number 4.8. So now you can't go to the shop and say, give me 4.8 pence. Right? You will say either give me 4 pence or you will say 5 pence. You may not have money to buy 5 pence. Right? And 4 pence, if you buy and sell somewhere, then you are not necessarily making the maximum profit. So any doubt so far? Asking at 9:15 that do you have doubt for a software is an unfair question. I completely understand. But in case if you have some doubt, I can help you clarify. Okay, so if we can quickly have a show of hands, how many of you have used MATLAB? Okay. Fine. How many of you have not used MATLAB ever? So we have a sum total of 3 people, 2 who have used MATLAB and 1 who has not used MATLAB out of 220. Okay, fine. That's okay. So can we go to that nonlinear programming problem?
Yes,
Yes, sir. It is very interesting, sir. You are teaching us very
Yes,
nicely,
sir.
sir.
Okay. So this is slightly quote unquote complex problem, but it is intentionally done in that way so that all the features of fmincon can be captured. Right? So I have a nonlinear programming. So the objective function, if you see, it is linear. x1, x2, x3, it is linear. This constraint, this constraint, this constraint, if you see, they are linear constraints. Right? So these are linear constraints. These three are nonlinear inequality. It does not have equality constraints. That is the only bad thing about this example. All of them are inequality constraint. But if you have equality constraint, it is the same way that you handled in linprog and int linprog. Right? Same way you need to find out their coefficients separately, coefficients of nonlinear constraints separately, coefficients of linear constraints separately. So here I have 8 variables, 1, 2, 3, and then this stands for 4, 5, 6, 7, 8. So I goes from 4 to 8, and for those variables, the lower and upper bound are 10 and 1000 over here. Right? So since I have linear constraints, let me first get rid of linear constraints. Right? So I am defining A. So these 3 constraints are to be captured, 1, 2, and 3 are to be captured in this A matrix, right? And I am deciding now that I am going to say arrange everything in the format x1, x2, x3, x4, x5, x6, x7, x8, and I am going to stick to this for the entire problem, right? So the first 3 constraints, if you see, they do not have 1, 2, 3, right? No 1, 2, 3 over there. So that is why you have this block as 0. And then whatever coefficient, minus 0, 0, 2, 5. So minus 0, 0, 2, 5. So x4 is there, x5 is not there. So 0. X6 is there, so 0.0025. No x7, no x8. Right? And over here, minus 1 is on this side. But we know that the constraint is of this form. The linear constraints are of this form. right? That right hand side, the constant term has to go in the right hand side. There is no place on it on the left hand side. So obviously you may say like, why can't I put 119, 111? So if I put 111, MATLAB will take it as 9 variables, that there are 9 variables. So only the variable should be on the left hand side. The constant coefficient should be on the right hand side for linear constraints, right? Here is where you need to be a little bit careful, that only for linear constraint, the right hand side has to be the constant number. For non-linear constraint, whether it is variable or parameter or value, everything has to be on the right hand side. So here I don't need to take this 8333 to the other side, right? So that we will see. So right now I have readily I can do A, readily I can do B, and readily I can also do my LB. So my LB is going to be lower bound. So it is going to be 100,000, because 100,000 x1 x2, and then from x3 also 1000, and for x4 to x8 it is going to be 10 10 10 4 5 6 7 8. So this is going to be my LB. So my UB is also going to be same thing. So straightforward x1 for x2 x3, and then 4 to 8 I will put 1000 1000 1000. So in this slide what I have majorly done is fixed my lower bound, fixed my upper bound, and then finish linear inequalities, right? If there had been a linear equalities, I would have finished that also. Okay, so this is the format in which MATLAB wants the problem. fmincon is the name of the function. Fun is the place where I have written my objective function, right? So for example, if I have x1 plus 2 x2 plus 3 x3, if you capture the coefficients, that is sufficient. If you capture 1 2 3, that means there is a unique way of writing that objective function. But now what I have is x1 square plus x2 x3 plus 10 times x2 to the power x5. So now if I capture just 1, 1 and 10, it is not sufficient, because I need to capture the non-linearity also. So now the coefficients no longer are sufficient. For linear programming, just the coefficients are sufficient. Since I have non-linearity, the coefficients are not sufficient. So I will write my objective function in some file. That file name I am going to give over here. So this is going to be a name of a file. X0 is going to be the initial guess, right? In linprog, there was no provision to give initial guess. In int linprog, there was a provision to give initial guess, but it was optional. Over here in nonlinear programming, it is mandatory to give initial guess. If I don't give an initial guess, it will not solve. So initial guess is required. Then I need to give A, B, which by now you are familiar with. A equality, B equality, again you are familiar with A equality, B equality, lower bound, upper bound, right? So these 2 plus 2, 4 plus 2, 6, these 6 have been following us from linprog. Nothing new over there. Linprog we used, int linprog we used, fmincon also, those 6 things are the same. And then I can for all my nonlinear constraints, I have to write a file in a specific format. We will discuss that format. What is that format? And then I have to have my options. Options is again optional. At least for this lecture, we are not going to look into options. So now my objective function, I am going to write a file, right? So since in this case it is straightforward, I could have written just x of 1 plus x of 2 plus x of 3, right? F is equal to, I could have done this, right? X of 3, right? Or I am doing this one, sum x 1 2 3, right? If I do sum x, this is wrong, because the objective function has only 3 variables, but the problem has 8 variables, right? So either I do this or I do this. This is wrong. F is equal to sum of x is wrong, because when MATLAB is going to evaluate this function, it is going to come with 8 variables. Now you will ask why it is coming with 8 variables. There are only 3 variables in objective function. That it will get to know only when it is inside the objective function, right? So when it comes to the objective function, it will come with all the 8 variables, values of all the 8 variables. So if I just give sum of x, it is going to be wrong, because my objective function is just the summation of 3 variables. So I have written a separate function, and this is the name of the function. Bit lengthy, but this is the name of the function. So that is going to be my first input argument. So instead of my fun, I am actually going to write at objective function, because that is the name I have given to that function. Right? I am writing another function file. This is what is the most critical part in fmincon. Right? So the name of the file I am defining nlcon, just to be comfortable with that it is non-linear constraint. So I am defining it with some name. This is also going to come with 8 variables. So x, it is going to have 8 values. How will MATLAB find out that there are 8 values? Depending upon your lower bound and upper bound, right? That in lower bound you would have given 8 values. So it knows that there are 8 variables. So it will come with 8 variables. And then, so input has to be this, name of the function and x, the decision variables. Output has to be 2 values. The first value corresponds to nonlinear inequalities. The second value corresponds to nonlinear equalities. In my problem, I don't have nonlinear equalities. So I have given C equal to is equal to empty bracket. So when it starts solving, it will first check whether this particular file, right, is giving me 2 output arguments. If I give this, then it has a problem. It will expect 2 output arguments. So whether it is required or not, I will have to give 2 output arguments, C and C equality. C is for nonlinear inequalities. CEQ is for nonlinear equalities. So right now I do not have nonlinear equalities. It is not there. So I have just given an empty bracket. I have nonlinear inequalities, right? So that I need to write. So everything, even if this minus 8333 was on this side, I'll have to bring it on the left hand side. That is the syntax of MATLAB. So here it has given the syntax C of x less than equal to 0, C equality of x less equal to 0. So right hand side has to be 0. Explicitly it is given. Over here explicitly it says B and B equality. So for linear constraints, the right hand side has to be the constant value. For non-linear constraint, variable or constant value does not matter. Everything comes in the left hand side. So here 100x1, so it is pretty much the same constraint I'm writing, 100x1 minus x1 x6 because of this 8333 into x4 and then the constant value. Similarly, the other constraint. The usual mistake that we do is we don't write x of 4, we write x4, right? But there is no variable called as x4. It is in the vector x, there is the fourth value, so x of 4. So this is my non-linear constraint. So objective function I have to write separately. Non-linear constraints I have to write separately. For writing non-linear constraints, there is a specific pattern that the output should have 2 values. Input 1 value. For objective function, there is a specific format, input 1 value, output also 1 value. Okay. So now it does not matter, even if I have 1000 constraints, this will remain C only, right? This will be C of 1, C of 2, C of 3, and then it will go all the way up to 1000 if I have 1000 constraints over here. And so now that piece by piece we have seen how to build the problem. Now that I have built the problem, I am going to dump everything into this fmincon. So I have fmincon over here. So what is my fun? Fun is I am defining here at objective function. So if this is confusing, then you remove this fun, directly write at objective function over here. Right? Same thing, if this is confusing, then you remove this non-lincon, directly write at nlcon. So first I need to say where my objective function is located. Then I need to say my initial guess. So initial guess, here I have taken my lower bound itself as initial guess. X0 is equal to LB. So that I have taken. A we know how to write, B we know how to write. So previously whatever discussion we had, that is A. And B, since it is 1 1 1 3 times, instead of writing 3 times 1 1 1, I am just using the inbuilt function once and I'm saying 3 rows 1 column. So it will basically give me 1 1 1 3 times. LB we discussed 100, 1000, 1000, and then instead of putting 5 times 10 10 10, I am just writing once into 1 comma 5, multiplying it by 10. Similarly, I am doing for upper bound. So lower bound is done, upper bound is done. So individually I have constructed whatever I want. and over here I am just dumping LB, UB. These two empty brackets because I do not have non-linear equalities, right? First thing is inequalities, then equalities for linear constraint. For non-linear constraint, everything will come in this particular file. So when I solve this, I will get this output. So this is the value of x1, x2 and so on, and this is going to be the value of the objective function. This is using fmincon. Again, fmincon does not support integer variables. So if you have integer variables and nonlinearity, then you need to rely on genetic algorithm. Otherwise, if you have only continuous variables, linear constraints along with nonlinear constraints, you can use fmincon. So any doubt in this fmincon? So the usual doubt is, how do I come up with my initial guess? Right?
Yes, sir.
The answer to that is that for right now I have randomly taken x1, x2, x3, x4, x5, right? So x1 to x8 does not have any physical meaning as of now in slide 38. But when you are solving a particular problem, you will have an idea what is the actual variable x4. It will have some physical significance. So from there you will be able to most likely say that rough idea you may have about the initial guess. If you do not have any idea about the initial guess, then what someone was suggesting, that you use something like genetic algorithm, wherein it does not ask you initial guess. You let it solve. From there, you will get a solution. At the end of that, you will get a solution. You take that particular solution and put it in fmincon. So rather than directly using fmincon first, I will first use GA, get that solution, and put that solution in fmincon. So any other question you have?
No, sir.
Okay, fine. So just give me 2 minutes. I'll just finish genetic algorithm also. It's pretty much exactly the same. Just one difference it has. This is pattern source. Okay. So this is an example for genetic algorithm, right? So again, you need to give it a function file wherein the objective function is being calculated. So that is for fun. And then here you need to give number of decision variables, right? In fmincon, it used to calculate the number of decision variables on its own. Here it asks you how many decision variables are there. In fmincon, instead of this, you ask for an initial guess. Here it is not asking for an initial guess. It asks how many variables are there. And same again, A and B. In the second problem that I have taken for solving genetic algorithm, I don't have inequality constraints, linear inequality, so I have given square brackets. Otherwise, if you have something, you need to frame A and B and then give that. Then you have equality constraints, which is the same that we did in fmincon, linprog, int linprog. LB, UB is also same thing. We did in linprog, int linprog, as well as in fmincon. Non-lincon, we have typically done, we did this only for fmincon. There is no need for this file in linprog and int linprog because everything is linear, right? And just change the name from fmincon to GA. It will give you a decision variable, value of the decision variable and the objective function file, right? So this GA is being solved for this particular problem. So this small problem, right? These two constraints I have, which are non-linear, and there is one linear inequality, linear equality, sorry, not inequality, linear equality. So this is the entire 3 files. So this is the final file which I will use for solving with GA. This is the objective function file, similar to what we constructed for fmincon. This is the same whatever we constructed for fmin_con for nonlinear constraints, and this is how I solve the problem GA. So this is what I am trying to code. So this greater than equal to 4, less than equal to 16, both of that, if you see over here, has come to the right hand side, right? That this particular constraint is also greater than equal to 4. So first I will make it as less than equal to 4, then I will bring 4 to this side. So I have a -4 when I convert the sign. Minus x1 square minus x2 square is less than equal to -4, and then when I bring that -4 to this side, it becomes +4. So that's how it is. So what you need to, like, what I'm trying to emphasize is that you need to follow its syntax, that the constraints need to be of less than equal to form. If it is greater than or equal to, you make it to less than equal to. So that is the first thing you need to remember. The second thing is that for linear constraints, equality or inequality does not matter. For linear constraints, the constant value will be on the right hand side. So ax is less than equal to b, a equal to x is less than b equal to. So the constant term on the right hand side. For nonlinear constraints, it is c of x is less than equal to 0, c equality of x is equal to 0. So the right hand side has to be 0. Right? If you have a constant term, bring it to the left hand side for nonlinear constraint. So that is one thing that you need to remember. And then pattern search is also kind of similar to GA, right? So you, instead of GA, you write pattern search. Pretty much everything is same. Fun, number of variables, inequality constraints for linear equality constraints, lower bound, upper bound, and nonlinear constraints written in a particular file. So instead of just calling GA, you just call pattern search. So someone had this doubt that I'm using GA, it is not giving me solution. So not much change. Instead of GA, try calling pattern search. Right? And it's not necessary that you need to use GA and then fmin_con. You can do the other way also. So from fmin_con, you get a solution. If you know an initial guess, you get a solution. You can use that as an initial population member in GA. And the last example is MINLP. So the problem is over here. So I have a continuous variable x and I have an integer binary variable 0, 1, right? So this is an MINLP. So I have continuous variable, I have integer variable, I have nonlinearity over here. So everything is satisfied. So it is an MINLP. So the way I used to solve GA is exactly same. GA, fun, we know it is the place where I have written my objective function. So I have to write this objective function. That's the only deal. And then number of decision variable. Here there are no linear constraints, right? So A is empty bracket, B is empty bracket, A equality is empty bracket, B equality is empty bracket. Lower bound, I have been given 0.5 and 0. So that is defined over here, 0.5 and 0. Upper bound is 1.5 and 1. 1.5 and 1. And this one is same. All the nonlinear constraint you write in one particular place. Just ensure that the right hand side is 0. If there is a constant parameter, you bring it to the left hand side. So for this problem, it is already less than equal to 0. If it was less than equal to 5, I'll take that 5 to the left hand side. -5 is less than equal to 0. So that -5 would reflect here also. So that file. And only thing you need to, new thing you are learning in this slide is int_con. Now this int_con is the same thing, the int_con you learned in intlin_prog. So I have two variables. For this particular problem, how I am arranging my variable is x, y. So first variable, second variable, right? And so I am saying int_con is 2. So that is what will come here. So only the second variable it will consider integer, because the first variable I am told that it is continuous. So that is why I did not write this. I did not write 1 and 2. Okay. So this connection gave up. So I don't think so I'll be able to write. Fine. Okay. So I am not writing 1 and 2 because only the second variable is integer. So 2, and it is rest of the things is same. That int_con you just need to call at the end.
The screen is not open.
So is it not visible now?
Sir, it is not visible. PPT not visible.
Just
Yes,
one
sir. No, not visible.
And then in that RNG, one function was that. What does that mean, sir? RNG.
Sure. I'll tell you. So except for that RNG, let us complete everything. I'll come to that RNG for those who are interested. Other than the RNG, any other doubt? Fine. Okay. So RNG story is a little bit lengthy story. So all this meta heuristic algorithms, right? So for example, RNG I have used only for pattern search and genetic algorithm. So those algorithms start with saying that do something randomly. So if I have 5 variables, right? So first point in first step of genetic algorithm, TLBO, all those algorithms is if I have 5 variables, let us say just for convenience, let me say all the 5 variables are between 0 and 10. Right. So first step is generate some 10 solutions in this domain. Right. Let's say 15 solutions in this domain, not to confuse with the number of solutions and the bound. So I do 2, 8.
The screen is not visible. What you're writing, we are unable to see.
Just 1 second, please. Is it okay now?
Yes, sir. It is visible now.
So the first step in genetic.
Again it went, sir. Again it went.
Okay. I think so. I have some connection problem, so I'll not be able to write. The moment I try to write, it is disconnecting me.
Okay, so without writing, even you say, sir, that what is the screen alone you bring it.
Okay. So in the screen, nothing is applicable. So you are able to see that, right?
Screen is not visible now, sir.
And sir, if possible, please share the PPT, sir, with the participants.
Sure. Yeah. So there
now
is
the screen is visible, sir.
Okay. Yeah, screen is visible,
but it goes very immediately. It goes.
Now it is not visible, sir. Not visible.
Not visible now. Once it comes and then immediately.
You can explain, sir. Only 2 minutes. You can explain, sir. No problem.
So okay.
Just
Anyway,
explain it, sir. Later on, you can share the PowerPoint slides.
So there is no PowerPoint slide. That, madam, you are going to cover TLBO, right?
No, sir. Those things, all the algorithms we are not covering, sir. Some of the applications sessions are there, sir.
Okay. So these algorithms, meta heuristic algorithm, their first step is to start with random solutions. Now let us say 2 of us are solving. I am solving and you are solving, and both of us are being told start with random solutions. So I will start with 2,5. You may start with 3,8. Right? I may reach a separate solution. I am doing the procedure correctly. I am not doing anything wrong. I am not making any mistake. I started with 2,4. You started with 5,8. I will end up with an objective function value of 25. You may end up with an objective value of 30. Right? Both of us did not make any mistake, but our final results are different because we started with different starting points. Is that okay till that point? Till that is understood?
Yes, sir.
Yes, sir.
Fine. So that is the first thing. So now what I can say is that I can, without solving, I will write some random result. Right? And if you ask me how did you get this result, I will say that I started with a random population. That population gave me this result. Whereas in reality, I did not solve at all. Correct? That's a wrong thing, right? So I want randomness, but I want that randomness to be controlled. Is it okay?
Yes, sir.
So RNG is a MATLAB function that governs how the random numbers are generated. So every time I need in genetic algorithm random number, I'll ask MATLAB to give me random numbers. I will not give 1000 random numbers. Whenever I want random number, I will tell MATLAB, give me random number. There are inbuilt functions for that. So those functions are governed by that RNG function. Right? RNG, if you remember, there are two inputs, RNG 2, twister. So I am asking MATLAB to do something randomly, but a software cannot do anything randomly, right? So what it actually does is it actually does a pseudo random number generation. There is an algorithm to generate the random number itself, right? So that algorithm needs a starting point. So that 2 what I am giving is that starting point. So I am telling MATLAB that give me a random number, but start with 2 and use the algorithm called as twister. So twister is an inbuilt algorithm. So if I want to set the random number, set the generation of random number, I am using that RNG function, RNG 2, twister. Now every time I do RNG 2, twister, the same set of random numbers will get generated. Is it okay? So if I give you now some result, I cannot tell that for the random numbers I started, it gave me this result. If I tell that, then your answer would be, what was the seed that you used? So then I will have to tell the seed that I used is 2. Then your question would be, which algorithm did you use in MATLAB for generating the random number? Then I will have to say twister. So now in your version of MATLAB, if the version is same, if the operating system is same, then with the same seed and with the same algorithm, the sequence of random numbers that you generate and the sequence of random numbers I generated will be the same. So this is to reproduce the results. So how to fix random number generator? So RNG is for random number generator. It has 2 input arguments. One is which seed to start. Another one is which algorithm to use. So as long as I use RNG 2, twister, it will give me the same set of random numbers. If I use RNG 3, twister, it will give me the same set of random numbers, which will be different from 2, twister. So before using genetic algorithm, I will fix my seed and the algorithm. So next time when I am solving, I will get the same result.
So other than twister, there are also many other algorithms.
There are other algorithms. So generation of random numbers, that itself is an area of research. How do I generate random numbers? So there are many algorithms. Twister is one of the popular algorithms, which is what I am used to using. So if you type help RNG in MATLAB, it will give you a list of all the other algorithms. Then obviously next question is to be, if it is giving me 5 algorithms, which algorithm is best algorithm? So if there was a best algorithm, then MATLAB will not carry the other 4 algorithms, right? So there is nothing which is proven that this algorithm is better than that algorithm. So they give you all the 4 or 5 algorithms. Whichever you want to use, you can use. Is it okay?
Yes, sir.
Yes, sir.
Fine. So if there is any other doubt, I can quickly address that.
Can you give me a small idea about the genetic algorithm like MOGA, MOGA?
Yeah. You want a rough idea about that?
Yes, sir. Yes, sir.
So multi-objective, what it does is, in multi-objective optimization, I have more than one objective function, and all the objective functions are equally important. If you tell me that F1 is more important than F2, then it is not a multi-objective optimization. It's not multi-objective optimization in the sense it is no longer difficult. Because you have told me that F1 is more important than F2, I will ignore F2 to start with. I will finish the business with F1, and after doing F1, I will do F2, right? But multi-objective optimization, when I say I have more than one objective, all the objectives are equally important for me, right? And pretty much everything what you have for single objective genetic algorithm, the same thing holds true for multi-objective genetic algorithm. But if there is a single objective, then it is easy to say. So for example, if I have 10 students in the class, and if I say the best students is going to be declared based on the total marks scored in the exam, then it is very easy, right? I will add the exam marks of all students, like all subjects for every student, and I will see whoever has scored the maximum. That is a single objective optimization problem, and the objective function is the total marks. But now if I say my objective function is performance in mathematics, physics, and chemistry, right? Who is the best student? Now you may have this problem that one student is very good in maths, one student is very good in physics, one student is very good in chemistry, and there may be another student who is moderately good in all of those. So between these four people, we cannot say who is the best. Right? That's a multi-objective optimization problem. That I have more than one objectives, and all the objectives are important. And in most cases, it will happen that you will not have one solution which is good in all the three objectives. So in physics, you have person A, chemistry, you have person C, in maths, you have person D who are good. So then it becomes a complex problem. As in now, first I need to decide among these four people, whom do I take for next generation? So there we have something called as non-dominated sorting. How do I decide which solutions are good when there are multiple objectives? So that's just a vague idea about multi-objective optimization. And genetic algorithm works pretty much the same thing. Crossover, mutation, because crossover and mutation is not dependent on the objective function. It is dependent on the solution, decision variables, right? So whatever you are doing 1 to 0, 0 to 1, you are cutting two solutions and swapping head and tail. All that is same for multi-objective optimization.
Then how to solve this multi-objective function, sir?
How to solve that multi-objective function? So there is a way to rank.
Madam, for those algorithms, we are having separate sessions, madam. Right? Because it is difficult to explain by sir within 5-10 minutes. These are algorithms. Right?
Yeah, actually that is better, because I will give you some idea and that
Yes,
person
yes.
will teach in a different version.
Yes.
Then it will kind of confuse you.
Able to discuss all the algorithms, right?
Okay.
Okay, ma'am. Okay.
Sir, thank you so much, sir, for a wonderful session.
Thank you. I mean, it's 9:30 and 165 people are here. It's just unbelievable.
So
I
much,
don't
sir.
remember
Thank
last
you for
week
valuable
people
time,
sitting
sir.
so
Thank you so
long.
much. Excellent session,
Thank you
sir.
very much.
Thank you, sir.
Thank you, sir. It's really very enriching, sir.
Okay.
So clearly you have
Thank you, sir.
defined all the
Thank you.
concepts of
Okay, nice, wonderful
Sure,
presentation, sir.
Thank you
sir.
so much, sir.
Thank you. Thank you very much.
Thank you, sir.
Thank you.
Sir, a small request, sir. Please share your YouTube video link, sir.
Sure, I will give you. This is my
And
email
also,
ID.
if
I am
possible,
typing.
please share the PPT also, sir.
So we will pass it to you. So
Thank you,
on
sir.
top
Thank
of that, if you need something, you can just drop me an email. Thank you.
Okay, sir. Thank you, sir. Good night, sir.